Hello and welcome to the Edge AI Summit. My name is Moses Macon and I am the producer for this event. Over the next 4 days, we will be diving into the challenge that is how high-performing AI can be deployed at the edge on resource-constrained devices, not necessarily connected to the cloud. You can use the event platform to network and engage in sessions with technologists who are making this into a reality, but also use the presentations, panels, and roundtables that are here for the next 4 days to ask them questions to demystify the nuances behind this all. Before I hand over to our keynote speaker, Joseph from Collins Aerospace, I'd like to remind you that we have a couple of very interesting roundtables today starting at 11 o'clock Pacific time, which is 7 p.m. in the UK. This is your chance to engage in some very interesting discussions and bring your thoughts and opinions to the table. There is a limited availability for this, so do book now to reserve your place. Furthermore, I want to say a big thank you to all of our sponsors, our speakers, and to you, the audience, for making this event possible. So without further ado, I'd like to hand over to Joseph to hear about utilizing graph learning at the edge, and remember to use the live discussion bar on Swapcard to ask your questions.
Hello, and welcome to my talk. My name is Joseph Engler, and I'm the Chief AI Scientist at Collins Aerospace. At Collins, I direct an artificial intelligence laboratory that seeks to create products and solutions for both internal and external customers of Collins. As you can imagine, we get to deal with some very cool technology and very cool algorithms. And one of the algorithms that we found to be most cool is the graph neural net. And so today I'm hoping to whet your appetite on how we can utilize graph neural nets and graph learning on edge devices and edge environments. I'll cover the basics of what a graph neural net is, and then we'll look at use cases for analyzing edge devices, environments of edge devices. We'll also look at use cases in which the graph neural net has been placed at the edge itself. And then we'll look at edge use cases for aerospace and defense with the edge environments. Traditional neural nets have been around for a couple of decades and have proven to be highly effective. Unfortunately, there are a few drawbacks, though, to the traditional neural nets, and one of them being that they require highly structured input. For example, if I want to build an image classifier and I have 1,000 images, those images could all be of different sizes, but I have to rescale each image so that they're all the same size to be able to pass through the network properly. And I may even have to take and turn them from color to grayscale if I want, to have one color channel instead of 3. If I wish to build a sentiment analysis classifier, I need to take my text or my speech, which is unstructured data, and convert it into some structured input that can be utilized by the typical traditional neural net. So I can take my text or my speech and embed it using Word2Vec or maybe a bag of words embedding, or much more recently the BERT encodings. However, traditional neural nets lack the ability to handle spatial temporal data, and that's where graph neural nets excel. Graph neural nets consider the topology of the graph itself and take that into account when building out the graph neural net itself. So chemical networks and protein networks can be ran through the graph neural net so that we better understand the interactions that take place between chemicals and proteins that are close to one another. Social networks are another area in which we can utilize graph neural nets very powerfully, because we could actually understand the topology of, let's say, friends within the Facebook. One of the neat things about graph neural nets is that they can be much smaller architecturally than a traditional neural net. If we think about GPT-2 and GPT-3 that have recently come out, we're talking billions to trillions of nodes, whereas graph neural nets have been proven to be able to perform very well with a smaller architecture. Now, an example of a graph neural net would be, let's say, a citation network. So if I wanted to create a citation network or a citation graph for academic papers in the domain of artificial intelligence, I could actually take the unstructured data of the article itself, and from that extract the authors and create a node on the graph for each author. I could create a node on the graph for each title of the paper. So if I had 3 different papers, I'd have 3 different nodes for representing titles. I could also create nodes that represent the article text embedding if I want to use that as a node, or otherwise I can use that as a feature of the title. And then I can create edges that join together the author and the paper, and the author and the co-authors. I can also extract from the references a very similar concept where we extract the authors in the titles and the text embeddings of the papers that are cited in the references. And then I could link the referenced author to the paper's author via an edge that may say cited, author 1 cited reference 1. So I can build out a very large and powerful graph, but how do I utilize it? Well, graphs actually utilize the topology of the graph via something we call the adjacency matrix. And the adjacency matrix utilizes the neighboring nodes to indicate interactions within the graph. So when nodes are close to one another, you'll find a 1 in the adjacency matrix. Otherwise, you'll find a 0. In addition to the adjacency matrix, we have a feature matrix where each node has a feature vector of whatever given length. And we pass both the feature matrix and the adjacency matrix into the graph neural net, thereby not only taking into account the vectors that represent the nodes, but also taking into account the topology of the network. So if I wanted to create a graph convolutional neural net, for example, I would create my adjacency matrix, and then I also create a degree rank matrix that basically talks about how often or how many links each node has to other nodes. And we put that on the diagonal. Now, graph neural nets are very similar to other neural nets in that they're defined by a series of differently parameterized layers which are applied successfully. Here, I'm showing the graph neural net simply because of the fact that that's most common, or the graph convolutional neural net because that's the most common, and that offers actually 2 very crucial advantages. First off, the graph location does not need to be inverted, which basically would incur an order n cubed computational cost. And additionally, the transformation specified by the n layers takes into account exactly the n-hop neighborhood of the nodes, thereby incorporating the problem's topological space much more effectively. So as I said, we would have the graph input, which is the adjacency matrix, possibly the degree rank matrix, as well as the feature vectors, and then we would pass them through various hidden layers, and finally have some sort of output that is structured based upon the problem we're trying to solve. Now, one of the advantages of having using the adjacency matrix and the understanding of neighbors of nodes is that we can actually share parameters from neighbor to neighbor. So there's actually the idea that we can aggregate the information from one neighbor going to the next neighbor, so that, for example, in this diagram here, node E can actually extract information about nodes A, B, C, and D because of the fact that they're neighbors of node E. Therefore, the feature vector of node E can actually be influenced by the feature vectors of its neighbors. And that allows us to better incorporate the topology of the network. So if you wish to read more about graph neural nets or learn more, I've given some references here, and I'm sure these slides will be available after the conference. But now I want to discuss graph neural nets for analysis of edge environments. So satellite traffic, IoT networks, even social IoT clustering can all be looked at as environments of edge devices. And I'm going to talk about two such environments. I'm going to talk about the satellite traffic optimization, and I'm going to look into IoT anomaly detection. In 2020, Lee et al. Proposed utilizing graph convolutional networks for optimal traffic allocation on satellite networks. Satellite traffic directly reflects the state of the network at any given point in time and is an extremely important index representing the operations of the network. And so optimization of the network traffic is critical for the effective operations, especially for low bandwidth devices and low power consumption devices. Historically, these networks have been optimized using linear methods such as moving average or ARIMA methods, as well as nonlinear methodologies such as support vector machines and recurrent neural networks. However, most of those lacked the spatial temporal nature of the networks. Instead, Lee et al. Decided to utilize a graph convolutional network that would actually bring in the topology of the network, would allow parameter sharing between the satellites, and then pass that information through a gated recurrent unit network to allow for a much more accurate time series prediction. They showed very effectively that this was highly possible with graphs, and utilized the graphs in a very efficient manner to actually produce very good results. This year, another paper came out discussing anomaly detection within a network of IoT devices. IoT sensors are by nature pretty independent. They're usually bandwidth restricted and often of low power consumption. That ontology can actually cause the sensors to be unaware of attacks on itself or other sensors that are topologically nearby. Historically, people have utilized deep learning, deep neural networks to model the network as a whole. They've also utilized statistical methods throughout this process. But with the deep learning and the statistical methods, there's been some problems. Typically, they're slow to detect and respond. Multiple sensors can actually be attacked long before the anomaly is actually discovered at the network level. So the goal here was to actually instead move prediction from the network-wide level down a little closer to the IoT devices, and so they would actually be operating basically at a topological layer one level higher than the device itself. And so these authors placed the agents at that one level higher location in the network, and then took and utilized agents on those devices to pass data into a graph neural net that shares information from the topological neighbors of each of the agents. This afforded a much faster detection and better independent control of the devices because of the fact that it moved from the entire network level down into the actual regions within the network. Now, we think about neural nets on edge devices as sometimes being quite challenging because of the power consumption to train the neural network on the device or possibly to deploy the device. However, graph neural nets have been proving to be very effective on edge devices. And I'm going to talk about a couple of cases here. In this case, both of these cases are related to autonomous driving or human interactive driving, and show how we can utilize graph neural nets on the edge. So in 2019, Beal and friends created a paper called graph neural nets for modeling traffic participant interactions, and the goal here was to actually understand the short-term behavior between traffic participants so that the devices could make intelligent decisions about how to move. Historically, these devices have dealt with more physics-based models or maneuver-based models where they consider specific maneuvers that the agent is trying to perform. Interaction-aware models have been built, as well as some machine learning models such as Monte Carlo tree search and recurrent neural nets, and even generative adversarial imitation learning has been utilized. However, most of those do not incorporate the spatial temporal network of the traffic participants around the agent itself. So the goal here was to accurately predict the traffic participants' behavior to better inform the agent's decision-making, and obviously to avoid any unwanted interactions between itself and its neighboring participants. And the method that the Yolo team used was to utilize a graph convolutional network and a graph attention network to perform the predictions. They actually brought the data in as a graph, building out the graph based upon the adjacency of other traffic participants, and tested their graphs against 2 real-world data sets and then compared those over 3 different benchmarks. And when they did so, they actually were able to receive an error reduction of up to 30% using the graph convolutional and the graph attention networks. In another paper similar, Gao and team in 2020 actually decided to take the look at traffic participant behavior, but look at it from a different sense. So normally autonomous driving utilizes LiDAR or rendered high definition maps to give a bird's eye view of the situation, and that normally incurs a high computational complexity. So in the past, LSTMs and social GANs have been considered as ways in which they could, predict traffic behavior or traffic participant behavior. But Gao and team decided to look at it a little bit differently. They decided to represent the intent of traffic participants as vectors rather than in the raster representation. In doing so, they created what they called VectorNet, which is a hierarchical graph neural net that first exploits the spatial locality of every individual and the road components represented by vectors rather than images, utilizing what they called polylines and subgraphs. Then they took those subgraphs and passed those into models of higher order interactions among all the components, again, being another graph. Using these 2 graphs in these multiple graph layers, Gao and team actually showed very good results. Next, I want to discuss graph neural nets and their use at the edge in aerospace. There's a lot of areas in which graph neural nets can play an important role within aerospace. In 2020, a paper came out talking about flight delays and how graph neural nets can be utilized to effectively predict flight delays. Flight delays can basically blur the efficiency of the aeronautical system and can present cascading effects throughout the day. One aircraft delay often impacts the times of other aircraft arriving or departing at the same airport, not to mention connecting flights and dissatisfied customers. Historically, flight delays have been modeled statistically and via Bayesian networks, and some have even tried reinforcement learning to predict taxi out time prediction. However, in all of these cases, overfitting has been a common problem and has produced poorer results than it should. So this paper actually decided to take the approach of they wanted to predict the flight departure delay time 3 hours prior to the scheduled departure time. And the way they did this is they created graph sequences by assigning edges to 2 nodes or 2 aircraft if they shared arrival and departure airports within a given window of time. They fed that graph then as a sequence, if you will, into a heterogeneous graph neural network with attention layers. And then from there, they have fed those results into a sequence level graph attention network so as to predict the departure time delay much more effectively. One of the problems we're considering is rapidly changing information environment. Due to the rapid changes that took place during the pandemic, not all information is up to date on the internet. If you travel to a specific location and wish to go out for supper, historically you would do a internet search or maybe talk to somebody on Facebook or a concierge or just word of mouth. But those information sources may not be up to date. Instead, experiences of users that are recent and current would be much more informative. So we could actually develop a knowledge graph for each locale based upon user experiences in real time. So as a user goes to a restaurant, if that restaurant is closed or is carry out only, that can be recorded in the knowledge graph. And then when users pass each other in transportation hubs, such as airports or train stations, the edge device could actually shed the specific knowledge graph for that locale with other users based upon itineraries that the edge device would know about. Then users coming into that transportation or into that locale would have the most up-to-date information they possibly could. And we could have at their fingertips then the ability to query these knowledge graphs and be much better informed without using internet searches or without, risking far outdated data. And that's my talk, and I thank you for your time, and I believe we'll go to question and answering.
Thank you so much for that really insightful presentation, Joseph. We now have a few minutes, only a few, for questions from the audience. So do remember to ask your questions on the Swapcard app in the live discussion bar. Joseph, to kick things off, how long have you been using graph learning at Collins Aerospace? Could you elaborate a little bit on that for us, please?
Yeah, so at Collins, we've been using graph neural nets for about 2.5 years. We've experimented more so using the graphs for memory-based intelligence within our enterprise AI, but we've expanded to looking at the edge devices as I talked with the commuter information system. Excuse me.
Brilliant. Thank you, Joseph. And one other question. You mentioned that you work with a lot of academics on this that you referenced in your slides, and also looking to the commercial side as well, the solution providers that help to deploy graph neural networks at the edge. Could you elaborate a little bit on how you look to work with them and what challenges you see them helping you overcome?
So when we're doing basic research, we like to involve the academic institutions and try and farm some of that out, but more so to work collaboratively with those that are basically at the bleeding edge. We're a smaller team overall. We're about 50 people total. So it's not easy for us to always be at cutting edge ourselves. And so by using the collaborative methodology when we're starting a basic research area, that really helps us proceed along rapidly. On the corporate side then, we're more looking at the application of it and the development, getting it into place into our products and our services.
That's brilliant. Thank you so much, Joseph. I'm afraid that's all we have time for, but we have the next presentation from FlexLogix happening in a couple of minutes. So what you can do is take a quick break if you'd like to, and we'll reconvene at hour. Joseph, thank you so much for being a fantastic keynote speaker. I hope you've enjoyed yourself. And just a quick reminder, we do have some really interesting roundtables where everyone can engage and discuss as a group, albeit we are virtual. It sort of replicates the feeling of physical, getting to network and meet some really interesting people like Joseph who are deploying AI at the edge and very much at the forefront of doing that. So Joseph, thank you so much once again, and look forward to speaking again shortly.
Thank you.
Okay, morning folks, and welcome to the second talk of the day, second keynote of the day, and I'm delighted to welcome back Cheng Wang, co-founder and senior VP of FlexLogix. Cheng has been one of our long-standing keynotes, both at the Edge AI Summit and the AI Hardware Summit. So Cheng, great to see you again. Looking forward to the talk. And this will be best of both worlds, an efficient, reconfigurable solution for inference acceleration. So Cheng is going to present now, and then we'll have some Q&A at the end. So drop the questions into that live discussion box in the bottom right-hand corner of your screen. And without further ado, Cheng, I will hand over to you.
Thank you very much, Ben. Yeah, it's good to be here. That was virtual this time. It's still very good to come here and to the fourth Edge AI Summit. And actually, since this is a keynote, I wanted to kind of celebrate the fact that we've going on for almost half a decade, because really what we've seen is a lot of things have evolved over the past times. You know, we started this whole conference because I think there was a lot of AI related companies, a lot of edge AI companies, a lot of AI hardware companies. And, you know, the AI application is still in its very, very early stage. But you will see that the evolution is both large in terms of how quickly it's scaling up, but also quickly in terms of how quickly some of these workloads are changing. So that's why today I kind of want to touch on, you know, how the landscape of the inference, especially the edge inference, has evolved a bit over the past almost decade, as we will see, and how a really flexible solution in this regard really aims to solve both worlds. You really have to be efficient at the current workload, but you have to be very kind of reconfigurable, flexible, future-proof for the workload that is to come, because these devices, especially edge devices, are going to be deployed for years, if not decades. So this flexibility is of utmost importance. In fact, just as important, if not more important, than to be able to run them super efficiently. So a quick background on FlexLogix for those of you who don't know us already. Let me try to advance this slide here. You know, so I did start this company with my co-founder, Jeff Tate, 7 years ago at this point. In fact, we started off as a reconfigurable computing company, and we still are very much a reconfigurable computing company. In fact, we have a first product line of reconfigurable logic cores, which we call eFPGA. It's like an embeddable FPGA core into your SoC. And that was the original product. In fact, that has been profitable as a business unit since last year and will continue to be so. And of course, we've been backed by some of the very best investors in Silicon Valley. So all that is already, you know, kind of under our belt. But of course, being a technologist, I was unable to just sit still. And about a few years ago, people started approaching us about, hey, can you use this embedded FPGA with a lot of DSP and Mac operations and target it toward an AI inference workload? That's when I started to look at it more seriously. And as good as we think we are at being fully flexible, like, you know, an on-chip FPGA is, I was eventually able to convince myself and then others that just using the FPGA fabric as is to use, especially edge inference workload, is not the best application. In fact, we need something more dedicated. We need to build a different product to target the efficiency and the flexibility requirement of the edge AI market. So as you can guess, the edge AI market is evolving just as quickly as the data center is training them, because all models that are trained ought to be deployed. But there's some fundamental limit in the models in the edge in the edge side. In particular, you know, we have to be able to partition the graph, because in a data center, as you could guess, the graph could simply be partitioned across multiple devices, multiple racks of servers, if you would like. And that is simply not something that we can do. I mean, maybe an edge server with a few devices running, you can partition the graph maybe by a factor of 10, but certainly in the further edge devices of these, you know, single chip solutions, you know, cameras, phones, small systems, you know, in factories, those are standalone systems with a single accelerator. So it will simply be very difficult to make a traditional FPGA or a lot of traditional architectures fit efficiently in the edge AI space, because we do not want to scale down the model, right? We want to be able to run the entire model that's been trained as is on the edge silicon, but at a tiny fraction of the area, the power, and the cost of these larger data center class chips. So that's kind of why we decided to start on this X1 product line, which we call the Inference X1 product line. And I'll kind of go into that in a little bit in the future. But since this is a keynote, let's take a step back first and see kind of how we've changed just in the recent decade. Probably in 50 years, we'll be looking at, the recent century. But right now, right, really the field of deep learning and for computer vision especially, it's something that came out with AlexNet in 2012, which is less than 10 years ago. And this was revolutionary, because up until now, it's always been difficult to figure out how to determine a Snoopy as a dog versus a Garfield as a cat. There is no way to program it through an algorithm that will basically determine something as fundamental as cats and dogs. But that kind of changed in 2012 when AlexNet first started employing multiple layers of basically what's considered filters in the scope of image processing, but deeper filters, deeper in terms of more than a few stages, but also, in fact, more than one stage is considered deep at that time. And also you will see that the filter has multiple, what we call features. That's like the channels of the picture. If you have a picture RGB coming in, that's 3 features, red, green, and blue. And then as it gets filtered, you will see that the image kind of gets downsampled to a smaller size, but the number of channels, features, has kind of gradually increased. And that's important, because that means it's gradually starting to going from holding raw data to information, right? That's kind of how you can view this like a human. Like you are not looking at a picture, like how many pixels it has, how many 100 by how many 100, but what object it has, and where is the object, what type of object, how large is the object, so on and so forth. And that's kind of what these features hold. But interestingly so, right? You look at these operator types, it is quite different from what you're used to today. You start with 11 by 11. Nobody uses 11 by 11 at this point. Even 5 by 5 is becoming less and less common. Fully connected layers we know today is terribly inefficient, and it's basically trying to be avoided. But still, right, these are the things that was considered good at the time. And it's got 8 layers. In fact, you can tell every layer is almost all different from the other, also different from today's world where we have some sets of repeat layers, because this gives the network scalability, as we'll see. And basically it's classified 1,000 classes of objects, which at that time considered extremely good prediction accuracy, because it's better than anything else that's come in its past life. And it's interesting, right? Because this entire groundbreaking graph uses less than 1 billion operations per inference, which is, in terms of tops that people love to speak of, this is 0.0007 tops per inference. And that's considered groundbreaking. Of course, that's about to change, but at that time, this was considered groundbreaking. So, it's too difficult to go through every year at a time. So let's jump forward by 3 years at a time, right? In ResNet 50, this industrially recognized benchmark, actually it's a graph that is 6 years old. That came out in 2015. Because this was trying to solve this problem of vanishing gradients, where training was very hard to stabilize. Therefore, what it does, it kind of have a main path where the signal propagates through, and then it has these arcs. And these arcs basically add residuals onto the graph. So when you see these arcs on the graph, it's actually an add operator in the end of it, followed by a ReLU. And this process is basically able to kind of incrementally add some residual or noise, some additional information onto the main graph as it goes through the stages of the graph. So actually the graph becomes much more stable, because you can start off the graph with all these residuals as zeros. And you basically have a simple graph that feeds through, and then you can add these residuals gradually by training them. But what's interesting here is you see the operator types have slightly reduced, in terms of the number of flavors, right? Of course, the numbers of operators have drastically increased, right? The ResNet 18 is the tiniest one. That's got 18 stages. It goes up to, I think, ResNet 151. There's a typo here I didn't fix. And the most common one is right in the middle, right? That's ResNet 50. And this basically allows you to trade off between accuracy and computation. And I think I briefly touched upon how, there have been repeat layers in these middle sections. And that's what this does, right? The ResNet 50 has fewer of these repeat layers than ResNet 151. But you'll see that the operator type have basically, with the exception of the first one, which is 7x7 stride of 2, have converged to 3x3s and 1x1s. And that is actually a trend that's still true pretty much today. And of course, there's max pooling and average pooling. There's some stride of 1s, mostly stride of 1s, a certain number of stride of 2s for a downsampling. And of course, it's a smaller, much smaller fully connected layer in the very end, only about a million weights, because it's about 1,000 by 1,000. And the activation is still 1,000 output class. It's the same as before, but obviously now the prediction accuracy is much better in their classification. And what's interesting is you will see the graph has grown from 0.7 billion operators per graph to something that ranges from 1 to 10 billion operators per graph. And that basically has grown by a factor of 10 in 3 years, more than Moore's law for sure. In fact, the trend continues because all these previous network graphs have been classification, which, although interesting, isn't extremely useful as is, because you could guess, if you have a security camera, you have a surveillance system, you have a traffic monitoring system, you have some kind of self-driving robots, cars, you name it, system, they have to be able to recognize where are the objects as they come into my field of vision and what are these objects. So, just requiring you to center and perfectly place the object before you can classify isn't very useful. So there's been a workaround with it, with SSD nets, but, in 2018, there has been a dedicated network. Actually, it started a few years before that, but Yolo V3 was a very popular one. And that's when we started to look into it very seriously. This is basically a detector, and a recognition engine. Now you can recognize objects as they come in. So as you can see, the type of operators have largely been the same. The layers have grown, in this case to 75 layers. So there are, tiny YOLOs that, it's about half of that, if not a third of that in terms of its number of layers. But obviously you pay a great price when you go to the tiny version of these models in terms of prediction accuracy. But what you do get is performance. And of course, what you will see in this case is for 608 by 608, which is, a good resolution. You're looking at another factor of 10 in terms of operations per inference. So now we're well into the hundreds of billion of operations in order to do one of these inferences. So basically, if we want to run this at the full resolution at full frame rate of say 20 frames per second, you need something, as you can do the math, of multiple throughput tops of inferences per second to get the inferences per second from your accelerator, which obviously, accounting for the efficiency, it results in actually a pretty good sized GPU, which is why we started to say, we need to do something to have something more specialized, much smaller, much lower cost for the inference market. So now actually things took a turn, because following this, 10x every 3-year trend, you will have guessed that by now we will be doing something that is, 1,000 tops per inference, going to an even larger, what we call a backbone. All those models that we showed you has multiple stages of deep neural network that builds up to a head. So all that stuff that builds up is considered a backbone. And backbones are important because it helps you process the data from these raw data with not many features into a lot of features across a much smaller digestible frame size, kind of like how a human will see it. And of course, most of these features, based on what the object and type of graph it is going to be, close to 0 or lower values, and then a lot more of them will have, a lot fewer of those will have interesting spikes of data, generally speaking. That's why some people are also looking at sparsity. But that's topic for a different conversation. So let's look at this detector 2020 for a second. So what happens here is that what was a very simple head, non-maximum suppression, some simple math operator that is easily done on the host versus the accelerator. Host just means the host processor can take care of them. In this case, though, we're going through multiple stages of encoding and decoding and prediction heads. All these are actually kind of borrowed from natural language processing when the data center graphs are doing large translations of, translating English to French or putting stuff in the shopping cart, just based on the words of the humans. So it's actually a very sophisticated model that's now being adopted to do computer vision. But what you will see here is that although this encoder and decoder have been drastically expanded, actually the number of operations per inference compared to the backbone is still smaller by about a factor of 10, not more. So these are not crazily compute intensive, but they are much more compute intensive than they were before. To a point that they can no longer be executed efficiently just on the CPU as, oh, this is just a simple head that we're just going to run afterwards. We actually start to have to accelerate this because otherwise a head process is going to bog down the entire process. As you can guess, a CPU is more than 100, if not 1,000x or more, less efficient than a dedicated accelerator, be it ASIC or flexible solution. So if you're 1,000x worse, but you have to do just a 10th the number of workload, that's going to need 100 times longer in terms of execution time, which will clearly become the dominating factor. And that's why we have to now first start detect head accelerator as well. But you will see that the nature of these operation, this computation, is very different from the traditional backbone operations. So we have to kind of take care of them in a more specialized way. And a lot of other accelerators, non-flexible accelerators, will not be able to take advantage of their architecture, non-flexible architecture, to run these more flexible workloads. So now with all these background knowledge under our belt, let's look into X1 very briefly. Some of you have seen these before. And basically, it is a dynamic TPU array of a lot of ways to wire up the hardware in multiple ways so that we can compute very close to memory. It's basically meant to give you ASIC level of performance, but obviously dynamically reconfigurable so that it can adapt itself to multiple new models. And it's designed for edge applications with batch of one processing. So basically, if we look into one of these 4 tiles on our chip, you will see that there's multiple layers of memories, and these are not meant as caches in the processor sense. These are more meant to be like compute, in-memory compute, so that there is multiple layers of memory for the hardware to organize so that it can get the memory and the compute as close to each other and get the activation summed up so that it can then be activated and routed back to memory. So you'll see the actual computation happens in these L0 places of the SRAM. Of course, that's where the heavy lifting is happening, but in terms of prefetching of the weights, it's done in the L1. In the load and store of the activations, it's done in the L2. And of course, all these are local to the tile, and which is local to the X1 TPU array. But then there is this DDR and PCIe that is outside that has to get DMA'd, and those are what we consider as L3 memories, which were not drawn here. And basically what this allows you to have is an adaptive, dynamically reconfigurable way to solve a multi-graph model. So for example, let's focus on one tile with 16 TPUs. How does it look like? Well, if we want to do, say, a 3x3 convolution layer, and we're not looking at window graphs for the moment, the window graph would operate on a 4x4 kernel, but this is simplified to just say, let's work on a 3x3 kernel. You will see that this, for example, we want to do a 3x3 by 64 into 64 output filters. Actually, that natively mapped to just 9 of these guys. And since we have 64 of 1D TPUs across 4 tiles, we can actually get, say, a parallel throughput of 7 rows per compute. But even if we do just 1 row per compute, right, in 64 clock period, we can do a 64 by 3 by 3 by 64 multiplication. Very efficient natively on this hardware. And, you know, because say in this case, it's a stride of 1, it's also very memory efficient because, you know, there's internal delay lines built into these 1D TPUs. You only have to feed in the memory from 3 locations for the 3 rows. And they have built-in delay lines to daisy chain themselves to compute the entire operation. So you can do, you know, multiple of these in parallel and still not consume enough DMA or memory bandwidth so that your DMA can still feed it. We have a very small memory attached to our chip, right? It is only a LPDDR4X with by 32, which is literally the smallest DDR that will sell you, you know, and you will see all the comparison that we make in terms of performance comparisons are made against, you know, GPU-based devices with 4, 8 pieces of memory that's much wider, also much higher rate, clock rated. But it's intentional for us to be low cost and small and low power, and therefore we design ourselves intentionally to have just a single memory interface. But you need it because you have to be able to store memory that are much larger than what you can store on the SRAM. And we don't want to be dominated by that bottleneck. So now on to the next piece of cartoon. You know, now let's see, we're done with this operation. Can we dynamically reconfigure ourselves to do the next operator? And say that is a 1-by-1 operator. And what you can do is, for example, in a 1-by-1 by 64 by 64, we can do 16 of these in parallel per tile. So 64 of these in parallel per array, you know. But if you want to do something larger, say 128 by 128, you can do 4 of these in parallel per tile. And 16 of these parallel per array. But it's more interesting if you look at through this graph is the TPUs can morph and connect itself in multiple ways, non-standard ways, to support operator with a lot of input channels and not a lot of output channels, or vice versa, because this is a fully programmable solution. And the compiler takes care of these, by the way. So you can always try to use the existing hardware in the most efficient way possible. And that's very important for us. So let's take a few steps into the future and see how that looks like for us. You know, all these things that we have talked about are what goes into the backbone so far. But what goes into the head in transformer is very different. As I've touched on before, it is much, you know, though the YOLO and the SSD, these object detection and recognitions, have a slightly more sophisticated head, it's processable on a CPU still. But transformer is orders of magnitude more complicated than that in terms of its head computation requirements. And the first part of it looks more like a backbone, like, oh, that's easy to accelerate. We're just taking the activation values and multiplying them by constant matrices. But the problem occurs on the next step, when we have this QKV that are all data dependent and they have to be convolved with each other. And that breaks a lot of architecture, because a lot of architecture have been designed to have these weights either statically sitting or loading in through a very slow process, then have activation roll through them. But in this case, both the weights and activations are rolling through the compute pipeline. And if the compute pipeline isn't designed to absorb the weights and the activations both efficiently, one of these is going to slow down. And that's the thing we're trying to avoid here. So how does X1 do it? Well, very interestingly, because of our reconfigurable solution, it does it very efficiently. There is, you know, dedicated soft logic that will take these activations from down below or up above anywhere in the L2 memory through the interconnect fabric into this L1 SRAM port, which then gets sent. Actually, it could be broadcasted to all these 1D TPUs L0 memories. So say that is one of the two, say Q, which is a weight-based activation or activation-based weight, I should call it that. And the other path, is like K and then Q is, you know, the other activation-based activation, which comes in the other side. Yeah, so then these two are multiplied together natively in the 1D TPU, and then it gets executed out and sent out to the soft logic, which can do the soft max operators also natively instead of the CPU, and then written out to the L2s. So X1 is really, you know, ideal for these operations because of its reconfigurability. It can dynamically load this activation data into the weight memory. It can broadcast these weights on an as-needed basis. And of course, the L2 memory can dynamically transpose data on an as-needed basis. So when you put all these things together, and just to wrap up here, you will see that what we really have built here is something that is just as flexible as a GPU or a CPU in terms of what model it can adapt itself to run. But it is far more efficient than them in a sense that it is very, very close to the efficiency that you get with a hardwired ASIC solution. Of course, the ASIC solution can run very limited models, while this can run so far every model under the sun, or most models that we care about in the CNN space. And it is designed to execute in batch of one, unlike these data center class accelerators. So this combination of in-memory, near-memory compute, and a fully flexible solution really gives it more than 2x advantage over GPUs. Sorry, the data here got lost here, but yeah, it gave it a huge advantage over GPUs, yet with near ASIC level of performance. And really, I want to invite you guys to see these in action. This is virtual. You're just going to have to contact our great sales team and our great AE team that will support you with your demos, with your evaluation through the process, because our X1 SDK is just coming up out the door, and we want to get customers to come play with this as much as possible. And you will see the entire tool flow of how your high-level graph go through the compiler, go through the runtime, and gets executed on the X1. If you are in Mountain View, California, or Austin, Texas, you can also come to our office to do some great demos, because we have those running pretty much around the clock in our office. So that's all. Thank you very much.
Okay, thanks, Cheng. Yeah, great talk as always. We are over time, but just one very quick question we'll squeeze in. So you mentioned efficiency a number of times in that presentation. Is it easy to quantify how efficient the Inference one is?
Yes, it is, especially for models like Yolo V3. You will see that our efficiency is on the order of 60 to 70% utilization, and that is pretty incredible. And in fact, I want to invite you guys to all do your own math, because most of these graphs, they will tell you what is the number of tops, or what is the number of operations, if it's in the tops, to do one inference of this graph. And you can compare that with the inferences per second of the hardware on whatever accelerator you are evaluating, and compare that with the tops that's been advertised. What you will see that is usually on the order of 20% or so on most of these other existing solutions. But you should really do the math. Just take the top of the number of the model, multiply by the inferences per second, and compare that with the theoretical maximum that they're advertising.
Okay, awesome. Thanks very much, Cheng. Brilliant talk. So yeah, do get in touch with Dane and the team for more info. And thanks again to Cheng. We'll see you soon.
Thank you. Bye-bye.
Hello and welcome back to the Edge AI Summit. Thank you all for joining today, whether it be quite early or quite late your time. Now we have the keynote panel hosted by Patrick. So Patrick, I'll hand over to you in a moment, but do remember to ask your questions in the live discussion bar of Swapcard. If you ask your question, it will be asked during the panel. So Patrick, over to you.
Hello, good morning, good afternoon, good evening, wherever you might be. Welcome to the Edge AI Summit and the panel on building scalable Edge AI systems. We'll just do a quick round of introduction. My name is Patrick. I run the AI division at Samsung SDS, where we do all sorts of artificial intelligence from natural language processing, time series forecasting, image processing. Ultimately, of course, many of these models live and get inferenced at the edge, and we'll discuss very soon what that is and how to do that. Let's go on to Srinivas.
Thanks, Patrick. I'm Rangan Sukumar, and my first name is Srinivas, the way Patrick called me. And I'm from Hewlett-Packard Enterprise. I'm the chief technologist for data and AI, and my job is to make sure I think ahead a year and a half to 3 years on what technology is coming our way, and therefore help our customers build systems towards those goals. So that's my job. I have a lot of fun doing that.
Moshe?
Yeah, so thank you, Patrick. I'm Moshe. I'm from DeepAI, a startup at Israel. I'm the CEO of the company, and at DeepAI, we develop technologies for efficient training. And by efficient, I mean like 2 orders of magnitude efficient training using int8 operations. So as I see it, int8 is a necessary ingredient in order to provide training as the edge. So not going back and forth to the cloud to do the training, but doing it locally as a standalone application at the edge.
Brandon?
Hi, I'm Brandon Gillis, the CEO of Luxonis. You might know us from the OpenCV AI kit. We make embedding human-like perception, so depth sensing AI and performance CV into tiny things. So for scale, unfortunately, I'm black on black on black, but here's the idea. So high resolution, high frame rate inference at the edge. And I'm quite excited about talking to Moshe about training on the edge too, because we're not doing that yet. But our goal is to make it easy to have human-like capabilities. So depth perception, intelligence of what objects are, so you can get combine that with depth to get the 3D position, and then computer vision functions that are really useful for orienting and figuring out how things move and where they are when you can't see them anymore.
Great, thank you. So as you can see, we have some very knowledgeable panel members here about all things edge and AI. To start off the discussion, I want to ask every one of the panelists, what is edge, right? It seems to be that everybody means something slightly different. So what does it mean to you, and where does all this variance of the term come from?
I might have the funniest answer.
You get to go first, Brandon. You get to go first then, Brandon.
So I've always viewed, in history, it's, the winner is who gets to write the history. In technology, it's who gets there first, right? So data center got here first, and the data center guys had to figure out a term to say what is not data center. So if anyone's a fan of Silicon Valley, and when they trained a machine learning app, a classifier for hot dog, not hot dog. So this game is data center, not data center, and not data center is kind of long. So they just called it edge. That's my view of grossly what edge is.
Yeah, I think I want to connect to what you are saying. Clearly, what is not on the cloud and not on the data center is an edge. And this, this includes, of course, edge like desktops and laptops and small servers and edge appliances, and ultimately all the way to the mobile phones and wearables. But from our experience with customers, some of them are defining edge as something not in the cloud. Maybe they have like data center on-prem, and they call it like an edge data center. So the term edge is related also to the fact that you are not on the cloud. You have like control on your system, you have everything is your own premises, and then some customers define this as their edge.
Interesting. So I'll give you the perspective of somebody that's not on the cloud and how we perceive edge, right? So for us, edge is a place where new data meets a decision-making model, right? And this could be a mobile phone, this could be a camera, this could be a microscope, this could be a car, could be a cell tower, could be space stations, it could be anything that's sitting behind a firewall in a hospital, you can name it, right? And then, of course, the data center as well, right? So the way we interpret technically what edge means to us is edge means computing under constraints. And the constraints could be one of four. The first one you can think of is being able to make real-time decisions where you don't have enough time to process it offline, or learning to make decisions when your connectivity is intermittent or is only asynchronous. And then you have limited form factor constraints where you have to pack something within a small size to put it on something that moves inside a car, for example. And then you're often limited in power on how much you have in terms of energy to spend on making those decisions. So for us, edge is computing under constraints.
Yeah, thank you guys. So you can see you ask three people, you get three different opinions. So
I can add another opinion if needed.
Go for it. Four opinions.
Yeah, so another opinion is that edge AI is like a combination, I would say, like of two mega trends. Like it's an edge computing and AI. So all the reasons for edge computing applies as well. So if you have like an application where privacy or security is the most important aspects, and this is a property of the edge. The edge provides you privacy because you don't send anything outside the organization. So even if you are working in a data center on your organization, still, if it's because of the privacy, if it's like the application motivation comes from privacy and security, then you are part of this like edge compute reasons to use this type of deployment. So it's always like the applicative viewpoint. What is the motivation for this type of deployment? So three people, four opinions.
They're all quite congruent, I would say, though, if you think through them. They're just kind of alternate ways to define, I think, a very similar thing.
Mm-hmm.
Yeah. So edge is still a term that's being defined. So to the audience, I guess, if you talk to anybody about edge, I think the first thing is to clear out what you and your conversation partner mean by that. Otherwise, you might be using the same vocabulary but talking about very different things. So on the one hand side, of course, we have the data center. That's a fairly well-defined term. But Brandon, I want to ask you, what is the difference in your mind between edge and embedded? That might be on the other end of the extreme.
Yeah, and these kind of have a spectrum as well, where we just talked about edge, where, I said data center and edge, where I really should have been saying cloud and edge. That's a better definition, right? Cloud and edge are on the opposite sides because you can have an edge data center. And actually, one of my friends focuses on cell towers. Cell towers was mentioned, and they do, I think it's like 1342U racks of servers. So a ton of servers, right? Taking, I think it's 700,000 watts, right? And that's edge because it's an edge data center, right? It's a data center that's at the base of a cell tower. And it is for that privacy or reducing network bandwidth or real-time nature, so forth. So embedded then is on the far spectrum of edge, right? You have cloud on one side, and then like maybe data centers kind of in the middle, and embedded's on one far side, which is what I held up in my intro, which is something that is, the extreme of tiny, right? But there is a range of embedded as well, where some embedded systems might even run Linux, but usually they're just a more constrained version of Linux that, has heavy sleep modes and power modes that allows them to sip power, maybe run out of battery for months or even years. So that's the range of embedded, and where edge can still mean very large and literally, hundreds of thousands of watts. Embedded usually stops at, let's say, 15 watts or 5 watts, or, depending on who you're talking to, some embedded folks, there's the same range with edge, but it starts smaller, right? So someone might define their maximum of embedded at 15 watts. Some might define it at 5. Some might define it at 0.1, right? And you'd have this same sort of panel discussion where it's all slightly different definitions depending on, how deeply embedded you are. But generally it means small, relatively low cost, low power, generally means it can boot up really quickly or have some sort of like sleep mode that allows it to conserve power and also reduce the amount of heat that it produces.
Yeah, that's great. Definitely, that would be edge under constraints. That was mentioned by Srinivas earlier, where we have to watch the hardware constraints when we want to design the software that runs on it. Moshe, what are some of the challenges in scaling edge?
Yeah, I think one of the differences between cloud and edge, what we discussed earlier is, cloud you have only one, like several vendors, but edge is everywhere. You have many deployments, many endpoints to work together, and each one of them is like encountering different type of data, slightly different version of the data and the statistics of the data. So the approach today for edge AI is to do the inference very close to the data source, of course, and then low power and low cost. But for the training, we have the approach of capturing the data, sending it to some central data center or to the cloud, because over there we need a lot of power, we need a lot of GPUs to do the training. So the approach is that we need to communicate everything to some powerful station. And I think this can be a real challenge for scaling edge applications, because once you have like 10 times more endpoints, then you have 10 times more bandwidth to this like centric point. And it becomes, even with the cloud, it becomes a lot of hassle to make sure everything flows nicely and there is no congestion in any points in the way. And the turnaround is also gets higher. So if you have to handle like just few endpoints, it's one thing. If you have to handle millions of endpoints in this approach, it can be very problematic. So I think the fact that we are working today, I'm sometimes call it like a broken application. One part of the application is at the edge, and the other side of the application, the retraining part, is running elsewhere in the cloud or in some data center. The fact that the application is running in two locations, and one of them is like at scale and the other one is centric one, this is a real challenge. And as I mentioned before, one of the challenges that DPI we are working on to solve. And this is just one direction, sending all the data and from many sources. And I think another challenge, even if you have like a training capability and every endpoint, and you can do the training, today training is in some sense is centric in a principal way. You need to see a lot of data from many sources to be diverse so that the system can train in a robust way. Now, once you solve the first problem that I discussed, like the challenge of not sending everything to a centric point, then you come up to the next level of questions, algorithmic questions, how you can train at the edge. You started from some baseline, but each endpoint is now starting to go into like some different path, and you want to make sure that everything is working well. Like you don't want overfitting, undesired overfitting at any point, and you want to still be able to synchronize between them at some level. So the algorithmic challenges are also very interesting in that aspect.
Yeah. So on the one hand, you have a many endpoints, and then there's also a diversity. So Srinivas, how can we deploy AI on that diversity of different edges?
That's a great question, right? And so the easiest way we see customers doing it is they go to a vendor that's already solved all these problems for them, right? So if you're looking for a video analytics solution, if you're looking for a natural language processing solution, so there's vendors that can offer you out of the box, white glove experience where you can take their answer and put it away. But then the next best option is where the complexity creeps in, like what Moshe is mentioning, right? So you either do it yourself or you go trust the open source software to do the work for you. The gap is just too big, and it's not easy the way we think about deploying it today. So, and it's not easy because you have to think about so many different aspects, right? You have to think about hardware, you have to think about software, you have to think about orchestration, And then you have to think about app development as well. So if you're an enterprise, if you're a company trying to implement AI on different edges, it could be different hardware for different types of edges. It could be different software. And the moment you think about scale, you have to orchestrate a complexity of devices from different vendors, different protocols, and so forth. And then from an app developer perspective, that needs to guarantee that the data is at the right place at the right time, you have to have all the APIs that make sure your data is with you, nobody's seeing it, there's security guarantees, privacy guarantees, etc. And so the typical way we think about, helping customers that want to do Edge AI is we ask a set of questions that help the design, right? So we think about how fast and big is your data that's going to stream in, and how complex is your decision-making model itself? Does it have to be deployed on the edge? What is your latency constraint? So are you expecting the answer the fastest possible, or can you wait a little while? And what does that look like for you? Do you want to track, measure accuracy decisions, or do you allow, is a single query latency better than batch query latency for you? There's a set of things that you have to think through, like what Moshe was mentioning, right? So given my data input sizes, given my model input sizes, given my power constraints, given my bandwidth constraints, is this system going to do the job that I expect it to do with the SLA metrics that I wanted to come through when I'm trying to make some money out of that system, right? So you have to make sure you're able to, one, have a plan towards building systems, and two, you're able to work backwards from, here is what's providing me ROI, here is how I would construct the system backwards. So the short answer is, start small and build towards scale rather than, thinking scale first.
Yeah, and I think one of those key phrases that jumps out to me is the job that I've intended for it to do, right? So in my mind, often, computers and data centers are general purpose, but edge is generally has a very specific purpose attached to it. And of course, one of the biggest purposes these days is things like autonomous vehicles, right? Where it's very clear. So Brandon, you're working in the depth sensing area. Why is there so much of that in edge applications?
Yeah, so I think Mr. Sukumar put it really well on the definition of edge. It's like where new data is generated. And the really incredible thing about AI is it allows us to quantize things and understand whether it's big data or small data in ways that would take the research community years otherwise, or maybe decades, or perhaps intractable problems. And that understanding can be on cloud data sets that already exist. A lot of that has been analyzed since like 2012. Google's replaced a ton of their algorithms. And so the new thing that's existing when we can do inference on the edge, and now with Mr. Mishali's company, training on the edge, is quantizing the physical world in real time. And so the reason that you end up with so much depth sensing is often you want to know where things are. So in the autonomous driving example, what you're quantizing is, where are all the other vehicles, where are the stop signs, where's the crosswalk, where's the kid on the crosswalk, where's the deer that's running at the vehicle, and so forth. All of that requires some way to eke out depth information, because depth is what gives you, XYZ position of everything. And that's also useful for self-localizing, using the depth information to be able to estimate as you're moving when you don't have GPS and so forth. So that's why you see it so much is it's tightly coupled with the opportunity here, which is just like IoT, there's huge IoT boom. That was sensing the physical world, but doing it, temperature, humidity, salinity, all those sorts of things, right? Motion sensors. This allows you to sense the physical world like a human can. And humans have two eyes, not just for redundancy. It certainly helps, but because we have live disparity depth sensing, right? And that's what allows us to, interact with the physical world, pick these up, manipulate them really easily, is we have that depth information, we have the intelligence, and then we also have a slew of other more algorithmic functions that allow us to perceive the world, like we have edge filtering built into our eyes. But depth is a core portion of it, just the pure depth sensing in addition to intelligence. That's how you can pick up something that you have no idea what it is, right? You can see it and what's this thing, right? It's the depth is what allows you to do that. And that's the huge opportunity of the edge. And like we were all talking about, it does become more application specific, right? You are interacting with the physical world in your given applications. And a lot of those are some form of robotic system, whether it's an autonomous vehicle, which is just a very big and heavy robotic system, or it's a forklift, or it's some other mechanism of quantizing the world where maybe you're not driving a robot, but you'll eventually probably actuate or take some action off of what's happening in the physical world.
Thank you, Brendan. I just want to remind the audience, if you have any questions, there is a live discussion bar in your app where you can type that in. And if you type in your question and tell me to whom you're asking it, that would be great. So we've heard, depth information is very important and a very popular thing for these systems. It's becoming clear that edge implies constraints on the one hand for most of us here, and maybe some sensor information as well. So it's clear that if we want to put AI on this edge thing, there's going to be a cooperation between the hardware components and the software components. So I'd like to ask Moshe, how can we co-design a system that has to have both hard and software working together?
Yeah, so, I think I would like to answer this like in two ways. So just at the point of history, most of the guys in the company are coming from a previous company called EasyChip. We developed over there like ASICs for network processing, completely different domain. And over there, the challenge was very similar. There's a power constraint. It's like very large ASICs, a lot of software stack on top of it, and everything has to play fast and accurate. For every packet that is coming in, you need to decide something and move on. And the software and the hardware co-design was a real key aspect of those systems to make it actually work. So when we started DeepAI, we thought it's going to be very similar in that aspect. So we need to do some co-design of software and hardware in order to allow very fast AI system that can work, in all levels. But what we found out along the way, I think it's a personal opinion, is that we also need a co-design from the data scientist side. Today, data scientists are guys that are working in very high levels, and they most of the time they are not aware of their decision, what is the impact of their decision. So for example, just give you like one example out of my mind, sigmoid, which is a very typical, or used to be typical activation function, is very difficult in hardware. So for a data scientist, it means nothing to change a sigmoid to some value or leaky value, which are much easier to implement, yeah? So I think today there is still a separation between the model and the data science aspects, and later on someone need to figure out how to deploy this in software and hardware. And what we really need is a co-design through the entire system. So choosing a model and that is right for the problem at hand. Sometimes data scientists would like to save another 0.5% of accuracy, and by that they take a much larger network that can take a lot of time to train and very difficult to deploy eventually. So you need to make a decision, a joint decision all over, from the data science to the algorithmic, to the algorithms that we use to do those networks, and then to the right combination of software and hardware. So my answer to this question is clearly, software and hardware it's clear that you need a co-design, but you also need the cooperation from the higher levels. And AI is quite a unique field in that aspect.
Yeah, thank you. So I'm definitely one of those data scientist guys. And I think, on the one hand, the willingness is there, but on the other hand, we also need to be educated. So calling a sigmoid function is a no-brainer oftentimes for software people. And then, in order for them to get it, that it's effortful on the hardware, that needs education. But of course, most of us have transitioned to ReLU activation functions in the recent decade. So if you guys are still using sigmoids, go read your articles. We have a question from the audience. Sohini, and I cannot pronounce your last name, sorry. What are some applications of edge AI in addition to autonomous vehicles? Who'd like to answer that?
I'll go with that one, if that's cool. There's all sorts of health and safety applications. So we talked about edge. Edge is, constrained. It has the advantage of real-time privacy, and all those conspire together when you know what something is. The most basic example is, wood chippers, right? So all sorts of stuff is just flying into a wood chipper. You can't just gate that, right? You can't turn a wood chipper off if a piece of wood goes into it. But with embedded or edge AI and spatial sensing, you can know when fingertips are going into the wood chipper. And unlike a table saw where they have the system, I don't know if you guys have seen it, back to the hot dog example, where when it hits the hot dog, the table saw will actually shut itself down. Wood chipper can't turn itself off that quickly. So wood chipper is an extreme example, but there's all sorts of interesting safety systems that are going to come out where you have this human-like perception, this basic first level human-like perception of like a really dangerous thing's about to happen, right? And it's like a subset of autonomous driving, but very industry specific. So I think Forbes put it well when they said there's going to be, a decade of discovery of this, right? Even if we just froze all machine learning techniques, which are at the basis of this, when coupled with depth sensing, some form of depth sensing, whether it's disparity depth or LiDAR or time of flight, there's going to be a decade of discovery of all the ways the industries can be impacted, even in safety systems alone, keeping people safe, because you can have the equivalent of a manager just like they're looking at the guy working on the wood chipper and just, like you're about to do something really bad. Obviously, a wood chipper is maybe a silly example, not to put your hand in a wood chipper, but there are more nuanced systems where there's rotational systems, there are complex states of machines, and you have to be quite trained to know that you're not doing something dangerous. And when you're working year after year, that can easily happen. So I've talked to folks where these safety systems are being implemented, and they're super stoked about them because they've seen guys who are very talented technicians who've spent over a decade working with machines, and then one error, an arm is broken. I think it was 67 places, right? Because it got pulled by the machine and it effectively has infinite torque. That's the one I'm most excited about. There are, as Forbes put it, there's just silently tons of these across industries, whether you get into sports or even tennis. We've seen like 10 different versions of ways you can benefit tennis. and it's because of that physical interaction with the world, whether it's understanding someone's pose or it's knowing how to clean and groom the court so folks don't have to do it themselves. And the list just goes on.
I think you can see many titles of verticals starting with smart something. So smart retail, smart manufacturing, also called industrial 4.0, and smart smart city. So everything that a human can do, and AI can do better. Then at a large scale, large scale of deployment, it can be beneficial. So for example, human can watch a system of cameras and watch for some anomaly or someone coming in, surveillance, etc. But AI can do it like better and at a larger scale. So this is an example from the smart city world or from the security domain. In industrial, you have like many machines on the manufacturing floor. And each one of them is, producing a different product and working in a different environment and different configuration, and just, tracking all of them to see if there is some anomaly going on, something is going to break down in the next hour or so. It's a task that human cannot do even at a large scale. You need a full corporate to watch those systems. So with AI at the edge, you can really do it, and in many cases do it better than human.
Yeah.
Just like 2 examples, go.
Yeah, and sometimes edge AI is hidden, right? So you don't realize you're using edge AI every time you change your channels, right? So for example, your voice-activated robot is using conversational AI that's sitting somewhere on the edge, right? So it's processing locally, it can do 100 things. So Siri is one. And then you can think about the other extreme as well. I talked about different edges. We have use cases where we work with the square kilometer array, for example. It's a distributed system. It's a telescope that captures petabytes a day. That's still an edge processing system because you're not going to be moving data between one telescope and another. You have to process them locally. It's tons of data and so forth. So there is the extreme case of, scientists doing one-off hero runs that are also edge AI. And then there is the daily uses where, you don't even know that you're doing it, but the AI is there for you when you need it, right? So there's an entire spectrum there. And I can think of one more use case in hospitals, for example, where, this was a pediatric example where as soon as a baby was born, some of them that have genetic mutations need answers about how long is that genetic code going to tell you if this person is going to survive the first 6 hours, right? And so having those kinds of models on the edge where you're processing an entire genome, which is a 650 gigabyte file, that's edge AI too, right? So there's all kinds of use cases that you can think about, different model sizes, different sample sizes, different types of data, and so forth. So
yeah, I think the mobile world is also very interesting because if you go, to the extreme of the edge, where a mobile device, each one of us have like at least one phone, then, for example, without doing any advertisement, Google just announced the Pixel 6 phone, and then if you go over the announcement, I think like half of it is about AI inside the phone. So, speech recognition get personalized for the user, and recommendations and everything now the phone is doing for you has also a tweak of AI doing it better for you. So it's clearly like the edge and useful on a daily basis for all of us.
Yeah, and I think the mobile example is a great one because they're leading this industry for edge. That's where edge AI was most beneficial the fastest, both computer vision, natural language processing, and so forth. And one other specific example, since you brought up medical, monitoring babies, specifically in the NICU, so preterm babies, with the combination of edge AI, spatial sensing, then computer vision, you can have the equivalent observational power of a professionally trained doctor to be able to see how is the baby moving, does it have certain tweaks that could be indicative of a neurological development disorder or lack of motion that could be, and you can quantize that all real time as if a doctor was just staring at the baby 24/7, which can just never happen. And with it being edge, you can now deploy this outside of a NICU. So when you have a high-risk baby, you can have better than NICU level monitoring as if the world's best doctor was just staring at the baby everywhere, because you're quantizing that data, and then you can get it down to text message size to send out privacy secure, just metrics of motion and so forth, breathing, frequency. You can even measure heart rate visually now, which is crazy because of the neural models behind it. So you can get all that data so that it becomes a force multiplier. And I think that's what all this is, right? It's all about becoming a force multiplier because it's things that humans can't do without this. And when you put all these edge systems out, then humans can do a lot more amazing things because they have the data that they would have to consume more than all of their time to produce if they were doing it manually.
That's really wonderful. So Sohini, I hope that answers your question. It was a pretty long list of possible applications, and I'm sure we could have listed a couple hundred more. So a very different question here from Daniel. In Daniel's experience, training of AI systems can, what he says, go off the rails and requires a good deal of babysitting. And he's having a hard time imagining how training at the edge would work. Can we help him out?
Yeah, it's an excellent question. Because once you bring the training option to the edge, then this type of questions are coming in. And so this is something that I mentioned earlier about the challenges in scaling edge application is the algorithmic challenge. Giving each endpoint the option to train without diverging from the desired path. So clearly we want each endpoint to do some personalization, some kind of adaptation to the endpoint, but we want it to be in a stable manner, in a way that does not forget anything that comes from the central model, does not go to some undesired, off the rail, as a guy asked. So this is an algorithmic challenge, and of course we are also working on this aspect as well, because there is a hardware aspect of giving the training at the edge, but also the software and the algorithm aspects of providing, I would say, a stable and reliable training at the edge. So you can deploy on multiple endpoints, and you still want to be sure that the base model that you put on each and every endpoint can go through some changes without worrying too much. And this is very different from training at the data center, where you train from scratch or doing like a large scale movement, I would say, on the data set. And then you have to babysit. You have to really make sure that everything is like cropped okay, and the augmentation and everything is like aligned okay. But when you're at the edge, you need some algorithm to ensure you that what you are doing at the edge is just small movements around the stable point that you started from. So you're not going to train from scratch at the edge. This is not, we are not, no one is trying to train ImageNet from scratch at the edge. This is not the problem at all. We want to start from some stable point and stay around in some personalized sense around that point.
Yeah. Right. So I guess the key word from AI here is transfer learning, to start from a pretty good model and just tweak it a little bit for that edge point. We do need to move on to our next question. It comes from Nitesh. I think this is very interesting. He says, if the edge AI hardware is going to be very application specific, then instead of expecting to see a single company in the future like Intel or NVIDIA dominating this market, should we rather expect a series of mid-sized companies dominating each one of the many particular application areas?
I definitely agree.
Yeah, I think that's the future. Yeah, I think that is the future, right? So I think what is going to happen is, so you're going to fall into three buckets of hardware/integrated offerings. So you're going to have feasibility specific designs, which is to say, I just need the model to work. I just need Edge AI to work. So find me all the pieces I can and I'll do it myself. And then you're going to get into a space of vendors that cost optimize things. So once all those do-it-yourself has emerged, there's a productization aspect where you can commoditize that solution as a cost-optimized offering. And then there's going to be the performance, highly optimized, ROI performance optimized solution, which is going to be for the bleeding edge people, right? So that, I think, is going to be the custom snowflake that one has to build. So there's opportunities for all three, as Nitesh was saying, right? So you're going to see people that do a lot of feasibility, and then a few of them are going to be commodity, and a lot of use cases that are the long tail, where you're competing against each other, right? So I see all three coming up, and heterogeneity winning towards the end.
Yeah, great. So it sounds like all of us agree that the series of mid-sized companies is going to be the future. We're coming up to the end of our session here, so I'd like to ask all three panelists to give a 1-minute summary of what we've talked about.
Okay, so I will start. I think what we have discussed is various aspects of the challenges for scalability at the edge, and what it implies on the software and the hardware and the data scientists to make it work. Edge is very different from the cloud. You know, AI started at the cloud because we needed the compute power to make it happen. These days we are facing with, you know, commercialization or productization of the problem. So we need to think about like different hardwares and how to make it work fast and efficient and without going back and forth to the cloud. So all these aspects are very interesting, and I think they will open a way to many companies dealing with the edge. And I think for us, it's very interesting because at the core heart, you need to break this dependency on the data center. You need to be able to run a standalone application at the edge with all the aspects of hardware, software, and algorithmic a part to make sure it works and stable and stays stable and accurate over time.
I'll hop on next. Oh, go ahead.
Go ahead, Brandon.
Okay. So I'm just stealing from Dr. Malik from OpenCV on this one, to be clear. But you know, I think a good way to summarize, you know, what we talked about, what is edge AI and what is the opportunity? I think it goes back to like, what is AI? And the question of like, well, what industries is it going to impact? That question is the same as electricity in, say, like the 1900s. What industries is electricity going to impact, right? It started with lighting. And so you could look at lighting as the equivalent of cloud right now, right? It's constrained to just that one thing. And as we bring it to the edge and we do all this hard work to make that actually function properly, it's going to have the same impact as electricity, right? Like AI is the new electricity. They're really hard problems to get it out of just lighting into everything else, right? But when we do that, it's just going to transform every industry.
Right. And so scaling AI, in my opinion, is about, having the right technology with the right components, running the right software at the right scale you need it, right? And so we talked about all of these aspects coming from hardware, software, algorithms. And then, when you think about deploying systems at scale, the unique things that you have to consider about how do you orchestrate from the edge to the cloud? And then how do you think about fleet management when you get to millions of devices? How do you program the where question that Brandon was asking, right? So if I'm going to be finding the where using 5 sensors, how does it work? If I'm going to answer the question with 50 sensors, how is it going to work, and so forth. So then, I think one of the things Moshe brought up was network security and privacy. So if you have to think about all of this, you're not an individual anymore, right? So you have to think about how does a team work on all of these problems and take a solution that actually produces the ROI that the business is going to sustain. I think that's an exciting future for scaling up edge AI.
Yeah, thank you very much to the panelists, and thank you for the audience for attending the panel and listening to us. I hope you have a great time for the rest of the summit in training the most important AI system in the most important edge device, namely the one between your ears. Have a good experience. Bye.
Thank you so much, Patrick, and everyone else on the panel. It was a really fascinating discussion. Before we move on to the next session, just a quick reminder from me. There are some really interesting roundtables happening at 11 o'clock Pacific time. That is 7 p.m. In the UK. So do book onto them. This is a chance for you to really network and have those really interactive conversations that you would do in person. But albeit we're virtual, and there's some really great value in connecting with all technologists from around the world dealing with all different types of systems and different aspects of edge AI, whatever your definition. So thank you so much, everyone, and see you soon for the next session.
Good morning, everyone. I'm sure a few of the attendees on the Pacific time have joined us over the last session or so. So thanks for joining us, for anyone that's dialing in for the first time, and welcome back for the other attendees that have already been with us this morning. Delighted the next session from Mahesh from Grey Matter Labs. We'll be focusing around Life Ready AI. And I'll be talking about the vision processor. So Mahesh, thanks for being with us, and over to you.
Thank you, Zach. Very nice to see you guys here in the session. Welcome to the Edge AI Summit. Of course, it's virtual. I'm talking to you live from the Pacific time zone. So today I'm going to spend some time talking about Life Ready AI. If there are three key takeaways from this presentation, they would be the following. So the first part, I'll talk about Life Ready AI. What is it about? Why should you care about Life Ready AI? And then, of course, how do you take advantage of Life Ready AI? What is it that you as a partner, you as a customer can then do based on the information I provide today? So let's get started. And there you go. So we at Grey Matter Labs are in the business of Life Ready AI, providing brain-inspired chips that behave like humans do. Artificial intelligence that enables your devices, your machines to behave naturally. And of course, you want to do that efficiently since you are at the edge. And this, of course, helps our customers save time, energy, and money. So Grey Matter Labs, we are a startup. We were founded in Paris based on a DARPA grant. And so we have a science center, a system and applications engineering team in Paris. We have a silicon design center in Eindhoven in the Netherlands, along with our SDK engineering. And then, of course, I'm based in Silicon Valley, where we have our product marketing, sales, and our CEO, and of course, customer solutions. So our ability to serve customers here in the US and also in Japan. So today, what we're going to talk about is how does Life Ready AI propel automation? So we strongly believe that adding accurate AI at the edge saves time, money, and more. So it helps people optimize their processes, reducing the energy footprint and enhancing productivity. At Grey Matter Labs, this is all our focus. This is what we do day in, day out. So to get started, let me kind of define for you what we mean by Life Ready AI for automation. So I have 5 key things listed here. So let's start at the top. So of course, when we talk about Life Ready, it actually reminds me of the conversation that was happening in the previous panel, right? People were discussing about what is the edge. And really, one of the key aspects I took away from that conversation, as pretty much everybody concluded on, was it's a constrained environment. So life is constrained, right? If you think about what life is, it's a constrained environment. We as humans operate with constraints. And of course, we have evolved to kind of operate within those constraints. And part about those responses is having real-time responses. So having ultra-low latency is for us one of the key requirements to enable Life-Ready AI for automation. And of course, today there's enough resources out there to provide the ultra-low latency, but they of course consume a lot of power. So it's not feasible to bring those, NVIDIA-type scale machines to the edge, to the endpoints. And so here, when I talk about an endpoint, it is of course the end device, right? Whether it's a camera, whether it's some sensor, whether it's a combination of the camera with your device, whether it's a robotic arm. So a number of these devices, which I call endpoint AI, and that's why low power matters there. And so, of course, these are kind of like the primary requirements to kind of help you get there. But again, since we're talking about AI, we want the accuracy, right? So of course, when as machine learning professionals, we are used to tackling jobs in the cloud. And because of the resources we have at hand, we're able to achieve high levels of accuracy. That's what essentially got this AI started. So we want to make sure that we are able to offer that same level of accuracy at the endpoints, so you can build robust products. And of course, all of this from a technical perspective is great, but in order to make that possible, we believe there are two additional ingredients that are needed, right? So you need an ecosystem, because we believe as a semiconductor provider, we can't do this alone. So we need an ecosystem to be able to deploy these devices in a meaningful fashion. And then of course, programmers, whether they are data scientists who are working with the models, or you have embedded programmers who are trying to integrate these devices into end products, programmability matters. So we want to enable that fast time to market. So we'll focus on these 5 elements throughout this presentation today. So to get started, of course, I'd like to introduce to you our vision inference processor, or the Gray VIP. This is what we call life-ready AI in silicon. So what does the Gray VIP look like? It is a silicon that's been designed for endpoint AI. To kind of talk about the key components as a system on chip, or a SoC, which is normally referred to, we have a patented Gray core, which is neuron flow enabled, and I'll talk about what neuron flow means. It is embedded with a dual core ARM M7, an application processor, so you can run some of your tasks on the SoC. Of course, since I mentioned endpoint AI, it has the capability to connect to cameras directly. So we offer dual MIPI RX and TX as part of the chipset. And in addition, of course, we have the standard high-speed interfaces and other serial interfaces, such as PCIe, USB, I2S, SPI, I2C, and so on. So full SoC basically designed for integration into your endpoint devices. And of course, from a performance perspective, our target is really to achieve 20x IPS per watt, which is inferences per second per watt in terms of efficiency compared to an NVIDIA NX. And we chose the NVIDIA NX primarily because we found that amongst the Jetson series that's available today for edge applications, the NX seems to offer the best efficiency. And so of course, we wanted to beat the best. So that's essentially what we're bringing to the table. So naturally, the fact that it is a compact silicon, so you can see the size on the left. I've compared it to a dime. This is the entire package, not just the silicon inside, but the actual package, which includes all the memory that would be needed. So imagine having this kind of capability for your edge devices, which means that you can enable endpoint AI cameras, tiny cameras with huge capabilities, and of course the traditional M.2 cards. And as you can see, the size of the chip even on the smallest of M.2 cards means that you could potentially even envision having multiple of these on a single card. So again, having this capability in terms of the performance and the size enables these compact designs for life-ready AI. To get started, we are of course offering hardware development kits. The feedback we receive from our customers, of course, we've been talking to our customers for over a year now, is that they fall into kind of 2 categories. One category are people who have their host systems. They're quite kind of experts in the AI machine learning field. They've been doing this with the NVIDIA, for example, or an Intel system, for example. And they'd just like to plug in your card, replace what they're using today to get the high efficiency. So they want something simple and easy to get started. And that's why we make the M.2 card available. And then there's another camp where people have been experimenting with AI. They're trying out different applications, different use cases. And so the idea is that they would like to have an out-of-box experience. So what do I mean by an out-of-box experience? The idea is that we're able to ship them a kit. They're able to put this together, have the SDK associated with this, connect your camera, connect your devices, and run your applications, essentially within a matter of minutes. And that's essentially what we're targeting for. So having a full end-to-end hardware development kit that has a camera which has a capability of doing both 2D and 3D, connected to a host board, which is a smart development board. And this allows for industrial-grade applications, supported with Linux. And then, of course, on the machine learning side, TensorFlow Keras, with APIs in Python and C++ to get you started. So that's what we call life-ready hardware development kits. And that's what we're making available to our customers and partners. As you can imagine, that's of course the hardware. In order to use this hardware, you need a ton of software. And so we call this the Greyflow SDK, the software development kit. It has, of course, the code libraries. We've been, have had about a couple of releases, now an alpha release and a beta release that we've been testing with some of our early customers. And so we've, put together documentation and tutorials based on this feedback, debugging capabilities, and of course the APIs that you can use. And I have some more details on the kinds of APIs that you would have access to. So essentially giving you a full end-to-end life-ready AI development kit with both the hardware and the software. All right, so what does the SDK look like? As you can imagine, there's multiple components to this SDK. We, of course, enable the typical machine learning frameworks. Today, we support TensorFlow Keras. There's been a lot of demand for PyTorch, and our engineers are working hard at it, so we will support PyTorch. You can think of the SDK broken down into 3 components. So we have the Greyflow Quick Start library. Essentially, that is a combination of the Model Zoo and tutorials for fast onboarding and deployment. And I have some more details regarding this, including also a session that we're doing specially on this. Then, of course, in the middle is the Greyflow ML Toolkit. You could think of essentially the data scientists out there who would salivate on this one, giving them the capability to tune, optimize, analyze, and of course, build your models so that they can run on the Greyflow architecture. And last but not least, of course, is the Runtime Ready. This is what takes you from kind of the data scientist world of the algorithmic world to the real world, which is on the embedded devices. So this gives you the capability to connect devices, download your model, and then also have some sample apps so that it's easy for you to get started. To give you a flavor for the Quick Start library, of course, we ship it with a Model Zoo. I typically refer to like the 3 elements of food, shelter, clothing for humans in life as classification, segmentation, and object detection. So, the 3 most commonly used models out there. And then, of course, we provide you multiple sets of models. So, you hear about people, some people like ResNet, some people like MobileNet, some people like EfficientNet, what have you. So the idea is to give you multiple sets of models so that you have, different flavors to get started based on your needs. These are, of course, trained on the standard databases like ImageNet, Coco, Kitty. So this gets you started really, really fast. And of course, it's not just all talk, it's not just all PowerPoint. So I invite you to come attend our 11 a.m. session where our architects, Selchuk and Diki, will walk you through an entire end-to-end flow with code and a demo that takes you from, starting from a Model Zoo model, which in this case, we do an object detection sample. We walk you through the ML toolkit. We walk you through the Runtime Ready library and download it, to our platform and then run the system. So it'd be great to have you guys for that session at the roundtable, which is at 11 a.m. We've been, of course, working with customers and partners to help fine-tune this. We welcome your feedback because we'd love to improve this further as we move into the marketplace. So please join us then. So, of course, that was a lot about the technology. So the key to, as we believe, the life-ready AI performance that we're able to offer is exploiting sparsity. And so what I show on top, which is the cartoon that you see, is how edge systems typically handle inferences. As in the case of a camera, for example, a GPU or an NPU is processing every pixel that's coming in. And of course, those top pictures represent frames, right? And on the right-hand side is kind of your neural network operating on every pixel that comes in. And so it's processing everything that comes in, right? Everything that it sees. We at Grey Matter Labs leverage our neuron flow technology, which is, of course, brain-inspired. And the key difference for us is that we process only the events that are changing. As you can imagine, life doesn't actually move that fast, right? Even when you think about it. So the key for us is to exploit this natural sparsity in life in such a way that is beneficial to you. And of course, you can take advantage of that in not only latency, but also in power and in accuracy. So we combine that sparsity with data flow parallelism. So it's a multi-core architecture. And here's where accuracy comes into the play. So, we hear about 8-bit int and how effective that is. What we found is indeed you can run models with 8-bit int. But in order to get kind of close to the accuracy that you're looking, in the cloud, we find that you're able to achieve that with 16-bit floating point max. And of course, there's a trade-off. Then you wonder, of course, you're spending more energy. But by utilizing sparsity and then combining it with 16-bit floating point max, we're able to give you the best of both worlds. We're able to give you the high accuracy, but also the low power and the low latency. And of course, we support this, industry standards in terms of floating point weights, so you can quantize your models and then take advantage of the system. We combine that, of course, with near memory processing. So like I mentioned, the chip, of course, includes all the memory that you need in terms of executing a model. So I won't bore you with the details of this, but essentially it's an event-driven system. So anything that changes triggers an event. That's what is passed on from one node to the other. And based on the memory architecture that we have, we are able to utilize this and reuse it based on only things that are changing. So this is an important piece of the architecture on why this works. Happy to answer more questions, of course, in the follow-up conversation. So to summarize, the three key architectural pillars for us is, of course, sparse processing, the idea that you respond only to events that change, bringing you benefits in latency, in power. The data flow parallelism, again, bringing you multiple benefits in terms of power, in terms of combining multiple operations at the same time. So that's the parallelism. And of course, the near memory processing to save power and bring you low latency, all at 16-bit floating point inferencing capabilities. So this, of course, allows us to empower these life-ready AI products to behave naturally with a low latency, interact meaningfully, and of course, save resources. So what could you do with this? So we've been, of course, speaking with a number of partners and customers through our journey, and it's just getting started. And what we found is really these low latency, low power capabilities allow us and our customers to build what we call the more reactive robots of the future. The more efficient envoy, the drones that, today as we're living in this COVID world, see more and more capabilities and more applications for these drones. And last but not least, a more intuitive companion where you can think of combining audio, video, other sensor processing capabilities that you would need to bring, all to bear so that you have a companion in the future that's, is responding to your needs. And like I mentioned, of course, all this would not be just possible by us, right? We are a silicon provider. We, of course, provide the software stack that's needed. But a big portion of what makes these life-ready AI products is the ecosystem. So we've announced a number of partnerships recently. As you can see the headlines over there. We believe there are a number of things that will make this ecosystem thrive. And key amongst them, for example, let's take the hardware development kit that we're providing. It's been possible because of our partnership with AD-Link, who brings, of course, multiple host platforms with different capabilities that you can easily integrate our module GreyVIP with. And of course, a 3D, 2D camera from Famous, which allows you to have industrial grade cameras ready to be deployed in real applications. Of course, what we also noticed was, as we were talking to a number of customers, that there's a big disparity in terms of the AI knowledge, in terms of how to use AI, and especially in the automation space. And as we were walking through and talking to our partners, talking to the ecosystem players, we realized that there was also a need for good education. And so, of course, we partnered with ERM in Paris to bring a life-ready AI kit for education. So this has been done in partnership with universities, with some of our partners, so that people understand the value of low latency, people understand the value of low power, but how do you all put that together and, make it work? So in that sense, we put together this educational kit so people can get started easily and quickly. And then, of course, there's a number of system integrators depending on the application. So in this case, we had a partnership with Easy Wheel. Think of autonomous mobile robots that are running around in warehouses. And so it's a very unique product that is enabled with LifeReady AI. So of course, I welcome, people out there who would want to participate in this ecosystem to definitely reach out. We do have a session on the ecosystem on Wednesday at 11 a.m. It's a panel session that's been organized as part of the Edge AI Summit. And during that session, Manuel, our product manager, will be happy to answer questions, and he also get into details of some of the ecosystem initiatives we have in place today. So I welcome you to join us there. So at a glance, again, so summarizing, basically, LifeReady AI is AI that feels alive, that is able to solve your real problems. It's enabled by Neuron Flow, our processor technology, which is uniquely optimized to exploit sparsity at the edge. The Grey VIP, of course, the full system on chip, providing you an out-of-box experience hardware development kit for which we're taking pre-orders today. And of course, the software development kit, which has been available for some time now, allows you to understand your models, take advantage of them with our hardware. And again, there'll be more details about the Greyflow software development platform later today at 11 a.m. So I invite you to join us there. So of course, a lot of our accomplishments have been recognized already. So we're quite happy about this. So, recently awarded the Ces Innovation Award 2022. And of course, at the Vision Summit in Stuttgart, we were the startup of the year. And so we continue to wow people with our capabilities and the products that we bring to the market. So look forward to doing that and continuing that process. So before I end, here's a short video. Okay. I'm happy to take questions. Let me stop sharing so I guess we can see you guys.
Thanks, Mesh. Thanks very much for that. It was an interesting session, and I'm loving the new branding that we've seen from you guys this year as well. I love that too. A couple of questions. We've got a couple of minutes. One question from an audience member was for you. Could you talk a little bit about the power consumption of the board?
Yeah, definitely. Absolutely. So as you saw, we have a small package. So essentially, this kind of package allows you for only up to a certain amount of power. So today, that package is rated at about 2 to 2.5 watts. So essentially, that's kind of the maximum power you would consume. But what we're finding is that for most of our use cases that we're working with customers, typically we are in the hundreds of milliwatts range, again, depending on the frame rate. So if you're operating at the higher end, 100 to 200 frames per second, you're in the few hundreds of milliwatts. If you're operating really more in the 30, 60 frames per second, you're looking at consuming less than 100 milliwatts. So,
okay. Yeah, you mentioned efficiency a couple of times, and I know that in the market, the efficiency of the computation is becoming a much more critical element. So, thanks for that.
Absolutely.
Next question, and one actually interesting one we were talking about before around the semiconductor shortage, the ongoing semiconductor shortage. So how's that affecting Grey Matter Labs, and what are you doing? You talked about limitations of life, and this is one of them, a big one for everyone that's having to work through. So how are you managing that and supporting your customers through the ongoing challenges?
Indeed. So so we started noticing these things happen earlier, like about 6 months ago, as we were, getting ready for our tape out, getting ready to, figure out the schedules for our customers and things like that. So what we found is that as, and that goes back to the partnerships that you create, right? So when we, we wanted to kind of come out with our partnerships, before, in fact, we are delivering, hardware development kits to our customers. So which meant that we had prior knowledge about what these partners were facing in terms of shortages, in terms of, lead times that were needed. And so essentially what we took kind of the approach was to, start working with our customers, working with our partners to understand early on, what's needed so we could prepare for them in advance and, make sure that they would have what they need in time so that they can do, what's needed, right? And so essentially it was a lot of planning, prepping, using the software development toolkit that we have today available to kind of get them going early on when hardware is not available so they can get, enough data to make decisions. And then, of course, then delivering to, their schedules and what they need. So it's a lot about pre-planning, working with our partners and, especially help, our partners have been extremely helpful, including guys like TSMC and others in terms of making sure our tape outs occurred in time and things like that. So yeah, it's been a lot of pre-planning essentially. So
sure. Some good work in dealing with some of the limitations of life, which is where you started. So
exactly.
Love that, Angie.
Yeah.
Cool. Okay, thanks. That's we're just past time, so we'll stop there, Mesh. But thanks very much for joining us. And as Mesh mentioned, running a roundtable at 11 o'clock Pacific. So invite everyone from this session to join that roundtable later on today. So we'll see you there.
See you there. Thank you very much.
Thanks, bye-bye.
Bye.
Hello and welcome back to the Edge AI Summit. I'm with Anoop Sahar of Siemens for his presentation. Do remember you can ask your questions to Anoop in the live discussion bar at the bottom right of your screen. But without further ado, I'm going to hand over to Anoop for his presentation. It's going to be very, very interesting about custom accelerators.
Hi, I am Anoop Saha from Siemens Digital Industries Software, and today I'm going to talk about how to build a custom hardware accelerator for your Edge AI application. Let's look at the context. AI has been part of our daily lives for a while now. One of the ways we interact with machine learning is through voice assistants. But even after a decade since they were first released, most voice assistants require an internet connection to work. If you look at the architecture of Siri, for example, it detects the wake word on the device and then streams it out to the cloud. And most of the natural language processing happens on the server side. There is a reason they created this architecture, and it is probably the most optimal for specific use case. Even though it has privacy concerns related to streaming all of our audio to the cloud, but this has worked fairly well. But there are cases where this architecture breaks down. You cannot do all of your machine learning on the cloud, especially now that we are living in an era where every device is becoming a smart device. Sensors have become so inexpensive and so powerful that IoT will be a $147 billion market by 2027. And all of these devices are capturing humongous amount of data. It is fundamentally not possible to even process that data, transfer or process that data on the cloud. So, and in many cases, it is not even, it fundamentally breaks down the use case of Edge AI. Self-driving car, autonomous driving, for example. Right? A single autonomous car generates 4,000 gigabytes of data every day. Now it has to process that data and decide on the path and decide on the decision, make those decisions with less than 1 millisecond of latency. There is no way they can send all of those videos or every other data to the cloud and then wait for the cloud to make that decision. Not only have to do that do they have to do that with low latency, but they have to ensure that it is done with a low power consumption. Essentially, your energy efficiency has to significantly improve in your Edge AI devices. But why is energy efficiency such a big concern? And that comes from the nature of the neural network computing itself. Now, most of you must be familiar here that neural networks are computational beasts. By that, I mean that even the most basic inference algorithm might have or will have billions of MAC operations, billions of multiply and accumulate operations per inference. And all of that requires complex processing of matrices and where you're fetching the data from the matrix and then operating on it and then deciding on the results. We looked at a variety of networks and looked at the compute infrastructure that we have on certain embedded devices to find out the source of the power consumption. What we found was probably not very surprising to anyone, but power is consumed in the storage element, in the storage of weights and biases in a memory. Power is consumed when we move the data from an off-chip memory to an on-chip compute element. And power is consumed in the ALU itself when we are doing certain computations, whether it is matrix multiplications, floating point multiplications, or other stuff related to that. So when we are talking about inference of energy optimization or improving energy efficiency for inference, we have to look at all of these factors. Essentially, the bigger the network, and more the computation of the elements in that network is, the higher will be the power consumption and the lower will be the energy efficiency in that network. So one way to improve energy efficiency is to just reduce the size of the model. And we can do it in various ways. And there is enough literature in academia, and there are enough certain companies who are doing it in a more automated way. We can do pruning, where we reduce the number of layers or number of nodes per layer after the training is done. We can do some type of smart encoding to reduce the storage of that model. We can leverage the caching architecture of that of the compute element to improve data localization, or we can do quantization. Quantization is nothing but using a lower precision data type than, for example, a 64-bit or 32-bit floating point number. The reason quantization works is if you think of inference, inference is mimicking what our brain is doing. And most likely our brain does not do floating point operations to detect whether a cat is a cat or whether a word or whether a command makes something in speech. And that's the core idea behind quantization. And all of this are purely software. Input is a network and output is a more optimized network. The second part of that is the implementation choices. And by implementation choices, you can, I mean the compute platform that you are using to make that computation. You can use a processor, which can be which is probably available in all the devices that I mentioned earlier. You can use a GPU. You can probably add a GPU to that device. A variety of off-the-shelf edge AI chips have come up in last year and a half, and they improve energy efficiency significantly compared to a processor. And you could use one of those, or you can build your own custom accelerator. As we go from left to right, our energy efficiency improves and our performance improves. However, our programmability has a significant constraint on it. You cannot, the programmability is significantly limited as we go from CPU to a custom accelerator. A processor is by definition fully programmable, and you can use it for multiple use cases. So let's look at the example, look at an example and see the actual impact of these in that example. So for example, we took the MNIST handwriting detection algorithm. It's fairly standard, not very complicated, and we choose an implementation called Lenet 5 by Jan LeCun. The code is available on his website as well as GitHub, and the original Lenet 5 takes around 1.25 million weights and consumes almost 5 megabytes of storage in the memory. Not a very large network, it's probably a smaller size network. But we use some of the techniques that I mentioned earlier of pruning and quantization aware training and other methods, like we use some encoding to optimize it. And in the end, we got a network which is less than 24,000 weights and consumes less than 10 kilobytes of memory in memory. A hopping 99.9% reduction in the size of that model. And accuracy is roughly the same. The original model has 99.1% accurate, and the new model was probably 98.8 or 98.7% accurate in detecting those handwriting databases. Remarkable improvement. But is that enough? That brings us to the second part of that equation. That what should be the hardware implementation of it? Traditionally, hardware innovation has always outpaced innovation in software. There are multiple reasons behind that, but one of the key factors is Moore's law, which states that you can pack twice as many transistors within a given area and every couple of years as you go down to a lower node. It's to the credit of the semiconductor industry, the designers, the chip makers, the design automation industry, the semiconductor manufacturing companies, and all of that Moore's law has consistently been true for last 4 or 5 decades. But what we are witnessing now is that scaling does not automatically translate to efficiency benefits. When we go to a lower node, it improves performance, improves more you can do in the next chip, but it does not guarantee a more energy efficient chip. There are a variety of reasons related to physics and architecture, computer architecture in it. But one way to mitigate that is to build custom domain specific accelerator. That is, you build specific architectures for specific type of workloads in specific domains. And that's why we are seeing an abundance of machine learning accelerators in last few years, because you cannot get that efficiency benefits just by Moore's law alone. But why is everybody in the world not doing these AI accelerators? And why is every algorithm not accelerated on the hardware? And reason for that is the traditional silicon design process. Silicon design is traditionally very expensive. It takes anywhere between $250 million to up to $400 million in NRE costs alone if you decide to do a chip, especially at the advanced nodes. It's not only expensive, but it's also very time consuming. Typically, a chip takes around 3 to 5 years from concept to production. And again, it's fairly slow, time consuming, iterative, and risk prone. One of the reasons that silicon design process is fairly primitive is because it is done at a abstraction layer called register transistor level, RTL. In RTL, you specify what happens in every clock cycle. Think of it as assembly language programming, which is also multi-threaded. Imagine the number of ways things can go wrong if your handshaking is not accurate or if there is a deadlock between different threads. Now, RTL has worked fairly well, but it increases the risk and makes it more error prone and increases the number of lines of code in your hardware. And one way to mitigate that is to use high-level synthesis. And the idea is fairly simple. Instead of writing what happens in every clock cycle, you write a C++ program which describes the functionality of the hardware. And then the compiler takes that high-level description and converts it into a model where it spreads it across multiple clock cycles and then further takes it down to a further multiple gates and creates the actual implementation of that silicon. HLS is not a new concept. It has been there for almost a decade or now or more than that, but it is specifically useful for creating these domain-specific accelerators. If you were at Hot Chips in 2019, NVIDIA talked about one of the chips that they did called RC18, which is a machine learning inference chip. But one of the key things that Bill Daly, the chief scientist, mentioned in an interview after the conference was the fact that they were able to do that chip with less than 10 engineers in 6 months. 5 people years. That's an order of magnitude improvement over traditional silicon design process. Significantly good. But improving the designer productivity or reducing the time is not the only value of high-level synthesis. One of the key challenges of building those accelerators that I was talking about is how to decide that you are creating the most optimal architecture. Because you can vary from a fully programmable, which is close to a processor, to a fully customized accelerator. In reality, your implementation will probably lie somewhere in between. And it's not just the hardware. You have to consider the configuration of that hardware, what type of resources that you are using, what type of compiler you would be using to convert that network into an accelerator, to run on an accelerator. How do you maximize data locality and resource utilization? And how do you interface with, let's say, a bus element? For example, what would the most optimal AXI bus ordering. And then how do you retrain that network? All of these requires you to make choices early on. In a traditional silicon design process, most of these decisions are made based on experience or intuition very early on the design cycle. And that does not always lead to a most efficient or most optimal hardware. Definitely not for hardware accelerators, which are customized for a specific use case. And that's where high-level synthesis comes up as a solution. Why? Because a single C++ program written in HLS, essentially written in a high level of abstraction, can generate multiple flavors of microarchitectures of the underlying implementation. You can vary those flavors, but just changing the parameters or using different optimizations in your high-level synthesis process. And once you have those different models or different types, microarchitectures, you can actually measure the performance, power, area, energy, and accuracy metrics of those different models. It's not just accelerators that is varying here. Every accelerator is usually part of a larger SoC. So to build the most optimal accelerator, you need to build that with the model of the rest of the SoC so that you optimize the entire system instead of just optimizing the accelerator. And this can again only be done when you are doing it at a higher level of abstraction, which also has a very high fidelity. And that's what the biggest value of high-level synthesis comes in designing custom accelerator. One of the key things that we use in our use case that I mentioned earlier was quantization. And how do you do quantization in C++? We do that using a specific data type called algorithmic C data type, which are just C++ classes which can model arbitrary precision data type from, let's say, 4-bit integer to a fixed bit or a floating point or a double precision or even a B float, which is Google's version of floating point architecture. And you can do it all in C++. You can run those simulations, and then you can figure out very quickly what is the most optimal quantization that you can use without sacrificing the accuracy. Typically, we have seen it works very well at a certain point, and then it falls off a cliff. And you need to find out that point early on using actual data and actual simulation data. Algorithmic C data type is open source and it is available in hlslips.org. And there are a variety of other goodies, open source goodies available that will help you build those accelerators. So in a sense, when you are building this accelerator, you have to think of the entire hardware and software together and then make those decisions to build the right system. You start with an implementation of network, you optimize it, you create the C application, you create the weights and biases file, and from there you measure the performance. We use the open source tool called ANET to estimate the performance of the hardware, and then we went through the hardware design process. Most of it is a matter of, just a couple of engineers. It's all exploratory that you are measuring what would the benefit of hardware acceleration for a specific algorithm. And many of these processes can be automated. I was talking about the Linux 5, right? What happens when we build a custom hardware accelerator out of it? I showed you how the just software optimizations improve the network size reduce the network size by 99.9%. And that reduction translated to 72x improvement in energy efficiency or energy per inference of that model. But when we built a custom hardware accelerator from that algorithm, we got a further 700x reduction in energy efficiency. In essence, from the original model running in software in an embedded device to a fully custom accelerator for that network, we got an improvement of 50,000x. And it took us just a couple of engineers working part-time for less than a month to get to that number. 5 or 6 order of magnitude improvement. Significant, and that's what the process we need to follow to build the custom hardware accelerator. And if you look at, I started out from talking about voice assistant. If you if you followed the news closely, you might have noticed that Apple released a newer version of Siri so that it works on the device now. But the reason they can do it is because of the underlying chip that is available on these latest iPhones or latest iPads. The Apple's neural engine, which is a machine learning accelerator available in this, just makes that possible. But you cannot create a very advanced, sophisticated engine for every gadget, for example. An assistive listening device, for example, that needs variety of machine learning techniques, but you need to do that at the power budget, which is less than 1 milliwatt, and at a cost so that it is still affordable to most of the people. And that's where the big challenge in AI in the edge comes from. So to summarize, machine learning is far too important to be all done only on the cloud. And when you are building a device or system for the edge, it's important to look at the entire system holistically, the hardware, the software, the application, and then optimize every component of that system to create the most efficient architecture. And lastly, these are new designs. We are doing new things, and they require new ways of doing those designs. And high-level synthesis not only improves design productivity by an order of magnitude, but enables design space exploration that helps you build a much more efficient accelerator for your design. Thank you so much for your time. I will now take some questions.
Thank you so much, Anoop. We are a little bit pressed for time. So Anoop, maybe a short, quick answer on this question. When comparing encoding, quantization, data localization, and pruning, and all the other ways to reduce model size, do you have a preferred method?
Oh, that's a great question, Moses. If I have to compare different ways to optimize the machine learning, I would always go with quantization first. And the reason for that is the value that we'll bring with quantization and identifying the right precision of data types is significantly higher than what we can do with pruning and removing the unused neurons or unused layers in this network. Especially when you're doing a hardware for inference, for example, a 32-bit multiplier is probably 16 times larger than 8-bit multiplier, and area is a big constraint. It's 225 times more power inefficient than, let's say, a 8-bit multiplier again. So those benefits are significantly higher with quantization, especially for inference.
And just contextualizing that to specific domains, you see that having a particular benefit in a specific domain, like, for example, autonomous driving or manufacturing?
Oh, that's a great question, actually. So if you look at different domains in which edge AI is applicable, I would prefer building custom accelerators in the domains where it is more mature than the other ones. So for example, vision. Vision has been there for a long time, and some of the algorithms are fairly optimized. So it's a perfect fit for vision algorithms. Speech is second. Natural language processing, I will wait till it gets a little bit more advanced. But specifically where you need to optimize for energy, that's where you get the value of building these custom accelerators.
That's brilliant. Thank you so much, Anoop. Anoop, thank you so much for a really fascinating presentation. You also have a roundtable tomorrow. Yes. So do tune in for that with some really interesting speakers on that, and that's an opportunity for you guys to ask questions and have a really great discussion with Siemens about this topic. So thank you so much, and see you in 5 minutes for the next session.
Thank you. Have a nice day.
So welcome back to our next session. So we're now joined by Ravi Kokku, who is co-founder and CTO of Merlin Mind. Today, Ravi is going to be discussing enabling edge NLP applications to work within challenging environments. So as always, if I could please ask you to pose your questions to Ravi in the live discussion box, which is at the bottom right hand of your screen. We'll be returning for some Q&A at the edge of the presentation. So without further ado, I'm going to hand over to Ravi.
Hello, everyone. It's a pleasure to be here at the Edge AI Summit, speaking about the work that we are doing at Merlin Mind to enable edge NLP applications in challenging environments. To start with a brief idea of our company is an AI solutions company whose goal is to make workplaces efficient through multimodal interfaces, including voice, and also automations enabled by AI. The first product that we are building is for classrooms that make teachers' workflows efficient. Specifically, our goal is to untether the teacher from the front of the classroom or from her desk and allow her to move around in a classroom. So in the rest of this talk, what I will do is define the classroom use case a little more detail and then talk about the different challenges that we needed to handle in order to make voice work in classrooms, especially with respect to classrooms being noisy environments, classrooms being very sensitive to personally identifiable information like voice, and classrooms also having bandwidth and latency constraints. Finally, I'll talk about the approach that we took in order to handle all these challenges. So let me start with a brief video that shows the overall use case and puts everything into perspective. This is a video from the perspective of a teacher in a classroom, in a K-12 classroom.
Teaching isn't a job for me, it's a calling. But what it means to teach keeps changing, just like the world keeps changing. Technology is a huge part of what I do now, and that isn't always easy. Hey Merlin, pair my laptop. Merlin is the perfect assistant. Being able to control the technology with just the sound of my voice is magical. Hey Merlin, open day one presentation. The less that stands between me and my students, the clearer our connection can be. And that's freedom for me, freedom to teach.
So the key problem we are addressing is cognitive overload on teachers. Today, if you see in classrooms, there is so much technology that is deployed. There are interactive whiteboards, there are teachers' laptops, teachers' computers, there are different kinds of HDMI devices, different kinds of USB devices like document cameras. There are also a number of student devices in the classroom. And any time that the teacher needs to spend on configuring any of those devices to be used during the teaching process is time away from teaching. Very similarly, there are also a number of applications that get used today in classrooms. And those applications, in order to interact with those applications, the teacher has to be associated with a particular device and keep interacting with that device. That device itself can essentially, in some sense, tether the teacher to that device. And that hinders the mobility of the teacher in the classroom. So our vision is to see if we can fix this cognitive overload because of so much technology and so many applications in the classroom. So imagine having a digital assistant in the classroom that basically integrates with all the different kinds of technology in the classroom and all the applications in the classroom and essentially voice enables them. That's our goal. So a teacher should be able to say from wherever she is, she should be able to say, hey Merlin, find videos of photosynthesis. Hey Merlin, switch to my tabs. Hey Merlin, switch to my laptop. Or hey Merlin, set a timer for 10 minutes, make a team of 4 students. So all these things, if a digital assistant can automate, it gives the required mobility for the teachers to be closer to the students, and it takes away a lot of load from the teachers. So that's our vision. Now, easier said than done. there are a number of challenges that we encounter specifically in classrooms in order to enable voice interfaces. The first and foremost challenge that we face in classrooms is noise. Classrooms are generally noisy. Classrooms generally have babble noise because of students talking all the time. Classrooms have HVACs, fans. It's in some sense an uncontrolled environment in terms of acoustics. And more importantly, classrooms, because it's a continuous speech environment, there is always instruction going on in the classroom. There is continuous speech. So when there is continuous speech and when there is a voice-enabled device, the device needs to make a decision which of that speech is for it, is targeted to it, and which of the speech it should be ignoring. The second challenge, and partly comes because of this continuous speech in the classroom, is this are the regulations around how voice data is treated. Voice data is generally considered personally identifiable information because especially there are K-12 schools are sensitive environments where there are children. Voice data needs to be treated carefully. The third challenge that we observe in schools is the significant diversity in bandwidth that's available in different classrooms. We have seen networks that are still with 802.11g with very relatively low bandwidth to all the way to 802.11ac and AX deployments where there is really high bandwidth, about gigabit per second bandwidth available in the environments. The final challenge with voice interactions is that voice interactions are very latency sensitive in the sense that during the teaching process, if the teacher says, "Hey Merlin, I need this," and then the system has to wait along, the teacher has to wait along because the system takes a lot of time, that's not the best experience that the teacher can have. It adds friction to the teaching process. So all these challenges really pushed us towards exploring an edge solution that brings together approaches to solve each of these problems that we identified. So the maximizing of processing of this data at the edge essentially provides the real-time responsiveness that we need. It also provides the needed privacy for the audio data, and it provides disruption tolerance to bandwidth fluctuations. So what did we really do, right? We built an Edge AI appliance, which is essentially an on-premise hub with high compute capacity. It has a 6-core processor. It has a powerful GPU and also a powerful neural processing unit. It has multiple HDMI ports and USB ports, essentially to act as a hub of integration for all the different technologies in the classroom. It also has a Wi-Fi and Bluetooth connectivity. It's built on custom operating system based on Android, and it also provides a lot of different third-party app integration so that it's easier to retrieve these applications and voice enable the applications through our device. It also has the ability to control the browser on teachers' devices. Now, the most important part that I would like to spend the rest of the talk on is the microphone part of it. As you can see in this picture, it's a 7-microphone array that we use for far-field voice processing, and the speech pipeline that is built that processes commands all the way from wake word recognition to the goal that each particular command specifies. So let me start with a very simplified voice pipeline architecture first. This is true with any digital assistant that provides a voice interface. The main goal of the digital assistant is to constantly look for a wake word, that basically something like "Hey Merlin" in our case. And then after that point, once it recognizes the wake word correctly, it starts listening for a command. Once the command is uttered, that command is sent to a speech recognition system which converts that speech into text. And that text is further processed to identify the intent and any additional information that is needed for completing that intent. And that information is passed on to an application which finally executes the command in context of what the application currently has. Now, if I dig a little deeper into this problem, the high-level goal of converting an utterance to the final goal that needs to be executed on a particular application gets divided into a speech signal processing part of it and text processing part of it. Within the speech signal processing, there are two goals. The first goal is to constantly be listening for wake word. And while it is listening, like I was telling about the different challenges that we encounter in classrooms, right, specifically with noises of different kinds, the microphone signal processing's goal is to remove as much noise as possible and provide a clean signal to a wake word detector. And the wake word detector's goal is just to look for the "Hey Merlin" utterance. After the wake word detection happens, the next phase, the next part of the signal goes to a speech recognizer, which basically is looking for the specific command. And the voice activity detection part of it looks for the end of that utterance so that there is high responsiveness. Once the utterance is cut to contain the command that the teacher has provided, the user has provided, that goes to a speech recognizer that converts it into text. Now at this point, what happens is speech recognizers typically end up having multiple alternatives given out as hypothesis, saying that it could be either this utterance or this utterance or this utterance. And this generally happens because generic acoustic models of speech recognizers don't necessarily have an idea of exactly the specific use cases. It's not a small vocabulary. Typically in the use cases that we are considering, we do need to support broad vocabulary because there could be file names with arbitrary names. There could be different kinds of concepts, educational concepts that teachers are looking for either on search or YouTube or any other kind of educational applications. So we need a broad vocabulary to be supported. That basically means that the kind of commands that we end up having to process, right, cannot be just one alternative, cannot always be accurate. So speech recognizers end up giving a set of alternatives from which we need to identify what the right one is. And that's where the next step, which is the first step of the text processing comes in, which is where we are identifying one among those alternatives which is the most appropriate to the current context, one or more which are appropriate to the current context. And that domain-specific reordering step really helps us a lot in improving the accuracy of the speech recognition step itself. After this point, we make the command go through, or we make the utterance in the text form go through a natural language understanding step, which is where the natural language understanding step also throws out multiple possibilities, saying that for each of these intents, it could be any of these goals. Typically in utterance, some utterances there is one intent, but in some utterances there could be more than one intent. The natural language understanding step just says, here are multiple possible goals of the user. And that is contextualized finally in the application. The application takes the final decision saying, which of these makes the most sense in my current context. This way of doing actually pushes up the accuracy of command execution for us. So let me run this end-to-end for one example to contextualize why each of these steps make sense in our case. So if I say one command, if I take one command as an example, pair my laptop, right? And in a far field scenario, a teacher says, pair my laptop, right? That goes through a speech recognizer, which could potentially interpret it as sell my laptop, where's my laptop, pair my laptop, right? There are a bunch of alternatives that the speech recognizer comes out, right? And some of these are actually real examples, right, of what we end up seeing in our system. The domain-specific reordering step basically says, among all these things, the most relevant one seems to be pair my laptop. It could be the second one also, which is where's my laptop, and the sell my laptop is lowest priority, because in this particular educational context, that doesn't make much sense. The next step in the natural language understanding for each of these alternatives, it comes up with what is the intent and what is the additional information. Like in the first case, it's a pairing device intent, and the device type is laptop. In the second case, it's a locate device intent, and it's a laptop. The device is a laptop. The final application basically makes a choice saying, okay, in the current context, pairing device and the type laptop makes the most sense, because I am not coded to support locating a laptop, and that's why the locate device laptop takes lower priority. So this, I hope, gives a high-level idea of how this entire pipeline makes the commands a lot more accurate in the context of classrooms. Now I'll go into a few results just to show the different improvements. I'll start with the microphone signal processing part of it. As I was saying, there is quite a bit of babble noise in the classrooms typically that we encounter. So in this picture, I'd like to show an example of how the signal processing can actually remove the babble noise and enhance the signal itself. So the first, if you look at the top part of it, this is with babble noise. Along with babble noise, there is a primary speaker speaking something, and the utterance get dwarfed by the babble noise. And what I see below, or what I show below, is a picture of the babble noise being removed, and the utterance ends up being a little higher in terms of the signal. So let me play the first one, and then I'll play the second, the processed one. So this kind of a signal is bad for both wake word and speech recognition. Now, with our microphone processing at the edge, you can actually see that most of the babble noise gets removed.
So they test DSPC processing. There is kindergarten noise playing from the noise speaker. It is 80 decibels at the microphone arrays.
So as you can see, the primary speaker's voice became a little louder than what it was in the previous case. And that is sufficient typically for the speech recognizers to recognize the audio. So now, so the next result I wanted to show is the post-processing of the alternatives and the speech pipeline benefit. So if you look at several examples that we end up supporting and what default ASRs end up giving out, right? You can see the different commands, like if I say pair my laptop, or if I say reduce, right? The default ASR output is radius, whereas one of the alternatives of what the ASR provided is reduced. And so our reordering step basically pulls that command up. Similarly, go home becomes bill home, right? And that bill home gets converted into go home, because it's still go home is still one of the alternatives that the ASR gives out, and we end up prioritizing it. So the table below shows for a large data set that we have been doing pilots or that has been collected as a part of our pilots, where the default ASR output, right, had a bit higher word error rate than the post-processing that that we do, and as a result improves the overall command accuracy. In fact, the command accuracy improves even at the NLU and the application contextualization stage, even if there are word error rates at the post-processing level. But this is just to give an idea of how post-processing ends up helping improving the accuracy of the overall system. And this system has been, we have been piloting the system for the last few months in different schools. We have been doing some amount of data processing to understand exactly what the usage patterns are. And over the last 4 months, for instance, if you see the table at the bottom, right, there are like 21,000 utterances in different classrooms. There have been 37 classrooms where teachers are using this device in 15 different schools. So in conclusion, we have started building domain-specific AI solution for the classrooms and realized that we had to do a lot of unique customizations for this particular environment. In general, we do want to explore these custom solutions for different domains, right? But this is a good starting point for us to understand all the different challenges. Specifically in classroom environments, there were quite a few challenges that came out, including a high amount of noise, background noise that we needed to take care of, privacy requirements in classrooms, bandwidth variations, and latency sensitivities, which pushed us towards developing an edge AI appliance for classrooms. But largely the way we build the technology is it's generic, and we can use it in other similar enterprise environments is the hope. So I'll stop here and happy to take any questions and share more of our story if you're interested. And you could write to me at the email address below.
Fantastic stuff, Ravi. Thanks very much for joining me back on stage. I think I've got a newfound respect after hearing that babble noise of teachers and what they go through on a daily basis. A couple of questions that I've had sent directly to myself, actually. So one of which is around the hardware considerations that you had for this product.
Yeah, so in fact, we had to try several hardware prototypes before we landed on this configuration, right? Because it took a lot of benchmarking effort to figure out what workloads are amenable and right. And in some sense, there are different optimizations that we wanted to do, right? Which had specific memory footprints, specific processing requirements, right? Both on the CPU, GPU, and so we went through 3 iterations and finally came to this configuration, right? Even now, it's like a constant optimization to see which parts of the software can actually start using the more parallel processing that the GPU and the neural processing unit provides, right? But yeah, I mean, it's a benchmarking exercise that we started right from the beginning and have been going on, right? Like cost is a big consideration, right? We want to make sure that we don't just ship hardware, right? It's like shipping dollars, right? If you just ship hardware that doesn't get used. So we wanted just that minimum configuration. At the same time, we also wanted to make sure that classrooms are very looking for very engaging experiences, especially with highly graphical, interactive, right, experiences, especially as classrooms are moving towards more and more web-enabled experiences, right? You don't know what you'll get into, right? Once you support a browser, they can go to any website. Like there's an application called Polar Globe, right, which actually really stresses on the GPU, right? So all those considerations saying, okay, what's the space we are getting into and what the workloads will be, right, really drove the hardware choices, right? So finally we landed on this, which is a 6-core processor. We think that it's decently provisioned that this product can remain in the field for a few years.
So with that, and you mentioned an interesting point there about the space that you're getting into. So a few of the other names in the space, you know, the likes of Siri's, Alexa's, Google's, things like that. How would you compete against them, and how do you kind of benchmark yourself against brands like that?
Yeah, it's a great question. Initially, in fact, if you go back to our history, right, we started with a study of all these existing assistants and how we could potentially even leverage them, right? And then we figured out that very soon there's so much different kinds of processing we need that we had to do quite a few things ourselves. And so we needed that control, right, in order to make sure that we really are nailing the accuracy in this, right, in this particular field. like Babel noise was a surprise for us, right? Like it's a constant chatter that keeps going on in classrooms, right? That was one challenge. The second one was privacy, right? How do you make sure that you have control of the data, right? That was a big thing, right? Yeah, and provisioning the hardware so that any applications, right? There are some schools that actually ask for integration with their own systems that are sitting in premises, right? So then you're potentially expecting that integrations are happening locally and right data actually flows in right from within their network, their own network. So all these needed a lot more flexibility for us. So rather than leveraging right an off-the-shelf solution, we had to build everything from scratch, right? So yeah, in terms of accuracy, yeah, I mean, technology has been going to such an extent that right we have similar tools as many of these other companies, right? So they are like state of the art in terms of accuracy that's possible in classrooms.
Yeah, of course. But I mean, that makes perfect sense of wanting to kind of bring that all in-house and having that control over it. So I think that brings us to about time, Ravi. So thank you very much for joining us. Some great insights there from you, and look forward to seeing you throughout the rest of the conference.
Yeah, thank you. Thanks, Ellis.